MLDAS 2021. MLDAS stands for Machine Learning and Data Analysis Symposium. And this is our 8th year, this collaboration with Boeing. And I would like to invite Dr. Ahmed El-Magamed, who's Executive Director of Qatar Computing Research Institute, to say a few words. So over to you, Dr. Ahmed.
Good evening, everyone. Warm greetings from Doha to all attendees and speakers. Welcome and thank you for being part of MLDAS 2021. Each year, MLDAS provides an opportunity for experts in AI and data science to pause and reflect on recent advances and open research questions and help us separate the hype from the substance. A platform for knowledge sharing and discussion, the focus of the symposium has always been to help tackle concrete challenges and problems. This year, keeping everyone's safety in mind, and with the support of Boeing, we have organized a virtual event with 14 different speakers who have made a name in their own fields. One positive side effect of the pandemic has been that we have an audience spanning over 30 countries. Now, in its 8th year, MLDAS has become a bona fide annual meeting for world-leading machine learning and data science researchers. I'd like to thank Boeing for their continued financial, technical, and logistics support to MLDAS for the last 8 years. We'd like to especially thank Bernie Dunn, President of Boeing Middle East, Turkey, and Africa. Thank you very much, Bernie. We appreciate all your support.
My great pleasure.
I would like to also thank Dragos Marinato, AI Chief Technologist at Boeing. He is the lead for research and technology, and Sanjay Chola, who is the research director and head of the Qatar Center for AI. I want to thank them both for their dedication in keeping the MLDAS flame going over the last 8 years. Along with our partners and collaborators, the speakers who have accepted our invitation to be part of this year's MLDAS and share their expertise, the organizers, we wish you all a very informative MLDAS 2021. I'd also like to thank Lawrence for all his local arrangements, support and help. And thank you all, and always keep safe.
Thank you, Dr. Ahmed, very much. Thank you. So Bernie, over to you.
Yeah, thank you, Sanjay, and hello to everybody out there. I'm speaking to you tonight from Dubai, our headquarters here for the region. It's a great pleasure to be with you tonight, wherever you are. Sanjay mentioned earlier that, so did Dr. Ahmed, that this is the 8th year of the MLDAS Symposium. And it occurs to me that this is, I believe, the 5th opportunity that I've had to provide opening remarks. And so it's really a great pleasure, and it's something that, you know, we've really now institutionalized every single year. It's really a pleasure for us to support this great effort. And I have just a couple of words for all of you. Though we were not able to gather face to face, we thought it was important now more than ever to bring some of the most important minds in machine learning and data analytics from around the world together. Thank you so much for being here. If this pandemic has taught us anything, it was how critical your work is to improving the status quo and to solving problems. There's no doubt that what you do will continue to play a larger role in our everyday lives. Boeing invests in the research and the engineering associated with the most recent advances in machine learning and artificial intelligence, from self-supervised learning to modern anomaly detection, and from adversarial learning to model-based reinforcement learning. We at Boeing apply these methods to improve internal process, but also to better support our customers, such as Qatar Airways, and for advancing the state-of-the-art in safe flight. You all may have followed last August the DARPA-sponsored Alpha Dogfight competition, an event that was broadcast live and received worldwide attention because of the challenging nature of the decision task. Boeing was represented in those trials by a Boeing Research and Technology group combined with Aurora Flight Sciences team, both from Boeing. In less than 9 months, our team developed an artificial intelligence reinforcement learning-based system that was highly praised by the attendees, the press, and DARPA, and was a semifinalist, losing only to the eventual winner, which was Heron Systems. Now, Boeing advances and invests significantly in the most modern engineering methods across all areas: aerospace engineering, manufacturing engineering, structure and materials engineering. And along with these, artificial intelligence engineering is making significant advances, as we will see from the talks during this symposium. Internally in research, the areas of robust machine learning and artificial intelligence are among our highest priorities. An illustration of that is Boeing's remarkable performance on the DARPA Assured Autonomy program that provides technical leadership in building assured and trusted approaches for tomorrow's artificial intelligence systems. To sum it up, robustness, assurance, trustworthiness are three of the key directions that Boeing is supporting and advancing in machine learning and in artificial intelligence. And we hope that this symposium helps to contribute to that. As we begin to kick off another symposium, I would just like to thank all of you for the work that you do to improve the world we live in and to help us better prepare and manage an ever-changing dynamic world. I'd like to particularly thank Dr. Ahmed El-Magarmed, Executive Director of QCRI, for the many years of fruitful collaboration between his organization and the Boeing company. Also, Dr. Sanjay and our good friend Dragos Martineau from the Boeing company. The Boeing and the QCRI teams that have worked very hard to make this event happen deserve express praise. I wish all of you productive and engaging discussions in the days ahead, and thank you very much for the opportunity to address you today.
Thank you, Amin.
Great. Thank you, Bernie. Dragos, over to you.
Lawrence, can you give me the share, please? I'm still grayed out, Lawrence. Yep. Welcome, everybody. Thank you so much for the introductory words, Dr. Ahmed and Bernie. Welcome to MLDAS. It's been a fantastic journey, and we're very happy to have the first virtual MLDAS. A couple of words. So I think one of the slides that we had on our first MLDAS was something like this. Now we start to understand the darkness around this. And as you know, this is a chart from Machine Learning 101, right? You have data, we build algorithms, and here come out the models. Well, I think that what you'll see in virtually all the talks at MLDAS is trying to make sense of this darkness which is around. We understand that data is not a given. We understand that that world around the models that we produce has its own uncertainty, its high dimensionality, its structure, its abstractions, and very important, something that we started to think about recently, timing. Everything has to be timed well. So I think the next few years will be probably dedicated to making sense of this world that is around our machine learning algorithms. More so now that we understand that for a system to work, it's not a single model. It's probably 2 models, 4 models, many models that come in to make either an autonomous system or a decision system to work. So I think over the next few days, you'll see a lot of attention to these 5 dimensions of the real world systems that we have to explore. And all this requires us to think beyond prediction, to think about inference, to think about causality, to think about the uncertainty of the real world, and again, about timing. So welcome. This is the schedule overview. Today, we'll have our first invited talk at 8:15 Pacific, 6:15 Qatar time. And we will follow then with the second, third, and fourth talk. And at the end of each day, we will have a question and answer session. These are some house rules for the attendees. So again, all attendees, when you join, you're muted. Please ask questions through the question and answer window that you have in WebEx. Our session chairs will monitor the questions, and we will ask the speakers the questions as time permits. We will also revisit the questions towards the end of the day in the question and answering sessions on each of the days. So again, enjoy MLDAS 2021. Thank you everybody for the efforts. Thank you for attending it and for making an effort. Thank you to QCRI for adjusting. I know it's evening in Qatar and, in Dubai. This way we can have North America, Europe at acceptable time. This was very generous from you to allow us to not attend in the middle of the night, Dr. Ahmed. That being said, I will get back to Sanjay. Make sure that the question and answers window works, please. You can test yourself, and I hope that everybody has a good MLDAS. If you have any issues, for example, if you can't hear or so, please send an email to or contact Lawrence, and he will try to connect you. I think so far we're good. So that being said, Sanjay, take it from here. And
great. Thank you, Dragos. So I guess without further ado, Andrew, you want to share your?
I would. Lawrence, can you enable screen sharing? That's great. Much appreciated. Can everybody see my screen okay?
Yes. So quickly, I'll introduce Andrew. Thank you very much, Andrew, for agreeing to give a talk here. Andrew Zolli is the Vice President of Global Impact Initiative at Planet, and he's also in charge of sustainability issues at Planet Labs. And we've been working with Andrew over the last few months, QCRI and Planet, over a project. And Andrew is also the author of Resilience, Why Things Bounce Back, a very famous best-selling book. And happy, Andrew, to have you over. And over to you. Thank you.
Thank you, Sanjay. Thank you, Bernie, for your support, and all of the organizers of this event. It's an honor to be here with you today. And thank you, Sanjay, for the introduction. I'll be giving what I think is the least theoretical, most applied talk. Today, I'd like to spend the next 30 minutes or so talking about how we can use remote sensing, advanced analytics, both supervised and unsupervised learning, sorry, if you are not speaking, could you mute? I'm getting a little bit of feedback on the line. So today, what I'd like to do is just talk a little bit about where we are in terms of our progress on planet Earth, and what our key sustainability challenges are, and how the combination of remote sensing and advanced analytics applied in the field by real people completing real complex management, decision support, prediction, and action tasks can work together, how these tools can work together to deliver real sustainability related outcomes. And in order to start that conversation, I just like to begin with the most basic. So this will be the least technical talk we have today about where we are now. And now I'll speak as an American. The first task is to figure out what the tasks are. And when we ask this question of many different kinds of stakeholders in the global sustainability system, we come up with answers that sort of broadly approximate this picture from The Wizard of Oz, which is to say we're in a tsunami of very complex planetary scale anthropogenic change right now. That is radiating in many ways and at many scales that are beyond the scope of everyday perception, but that are no doubt extraordinarily impactful. We are in a decade in which we now have less than 10 years to avoid locking in the worst effects of climate change, according to the Intergovernmental Panel on Climate Change, convened under the United Nations. According to IPBES, and the Convention on Biological Diversity, there are more than 1 million species which are right now on the verge of extinction. These two fundamental challenges, the challenge of climate change and the challenge of the loss of nature, represent civilizational scale events, much larger than our everyday cognition. A big part of that is because humanity has now terraformed 75% of the planet. This is our principal ecological function on Earth. We transform forests into pasture lands, into cities, into places where we extract resources on a sustained and ever expanding basis. Indeed, today we use more than 1/3 of the world's land just for cultivating crops and livestock. And the pressures that those activities place on the remaining wild places of the earth increase the intersections and interactions between wildlife, domesticated livestock, and humans, and lead to increased disease prevalence and the transmission of zoonotic disease that spends some portion of its life cycle in wildlife or in other animals other than humans. And of course, we've all been living in the last 15 months or so, last year, with the effects of this pandemic. And this is, while we tend to think about the pandemic as a public health risk, it is indeed actually an ecological risk. It originates in the relationship between human beings and nature. We've transformed half of the world's oceans, and fisheries are declining worldwide. We've changed the kind of population structure and basic biodiversity of about half of the world's oceans. And in some cases, the world's self-replenishing fisheries are on a target to be completely lost by the middle of the century. And all of the changes that I've just been describing are really the ones that we know about before the next billion people, the next billion human beings show up in the next decade. And so, we've got an extraordinary burden taking care of the human beings on planet Earth. Now we're going to be adding, another 1/9 of humanity to the picture just in the next 10 years. In all of this, data, AI, and analytics will be absolutely essential. If we are not to cut down all of the world's forests, if we are not to fundamentally attack and transform the essential life-giving systems that make life on Earth possible, data and analytics will be absolutely essential for our understanding, measuring, making, and illuminating risk, improving our output, increasing our ecological efficiency of all of our actions, conserving nature, and lifting people out of poverty. This is an enormous hat trick for us. We've got to accommodate the needs and aspirations of a huge human population while de-intensifying the impact that we have on those systems that make life on Earth and flourishing on Earth possible. And the very tools that will be discussed here at MLDAS over the course of the next several days are the kinds of core technologies that are going to make that possible. When we look out over any of the human activities, but we'll start very simply with agriculture. In this century, the more information we can bring to a problem, the greater the reductions in ecological intensivity. We sort of think about information, AI, analytics, guiding decisions and enabling us to predict where things will go next, enabling us to make decisions which increase the yield, increase the outputs, and do so in a way that diminishes their impacts on the world. So the challenge here, of course, is what's happened just in the last year. If you look at national statistical offices, the kinds of governmental agencies that collect, say, basic agricultural statistics, what you find around the world is that COVID has stopped data collection all around the world, particularly in some of the low and middle income countries around the world, where it's simply arrested the ability of observers to go out and data collectors to collect ground truth information. 96% of national statistical offices from governments around the world have fully or partially stopped collecting information on the ground. So if we are to catch up to the burdens of this decade, we're going to have to augment this ground collection with the continuous observation of other kinds of sensors in the ground, in situ sensors, sensors in the sky, sensors in space. And that's what our organization, Planet, actually works on. We're probably best known for having deployed the largest constellation currently of Earth observing satellites in history. Most of them are very small. We have two principal modes of our constellation. One of them here, the sort of canonical one, are referred to as doves. They're very small satellites about the size of a loaf of bread. We've put hundreds of them into orbit in a specialized orbit that runs from pole to pole, sort of synchronous with what we call a sun synchronous orbit. These are satellites that come over the North Pole, down over the equator, down over the South Pole, and then spin up over the dark side of the Earth. As the Earth turns perpendicularly underneath them, they collectively image the entire terrestrial surface of the Earth every day at a little more than 3 meters per pixel. We have a companion set of satellites that can then zoom in, and not everywhere on Earth, but anywhere on Earth, multiple times a day at roughly 50 centimeters per pixel. And we use the two systems interchangeably. One of the most important places where we use artificial intelligence and supervised learning classification systems is in detecting anomalies in the 3-meter data and then using the higher resolution satellites to disambiguate. What we then do is collect all of that information, bring it to the ground, and run it through a series of computer vision and supervised learning techniques that today find all of the roads and buildings at that medium resolution worldwide. So what you're looking at here, I'll just start that animation over again. What you're looking at here is our offices in San Francisco, or our neighborhood in San Francisco, the buildings in blue, the roads in red, and we're able to collect the Earth every day and then run those analytics at scale every day. And our overall mission is to use that combination of data and analytics to understand change at very high density time series. And the reason that that's valuable, I'll show you, is related to a whole series of sustainable development related challenges. Speaking of which, we've had an independent assessment done of the relevance of this ability to collect daily information on the Earth at high resolution to the Sustainable Development Goals and to the dozens of targets and indicators under specific SDGs. I'm going to give you a couple of examples in a moment of where we use these tools. But today, this data is relevant to measuring 14 of the 17 SDGs specific targets and indicators under a wide variety of them. That's why that observation about the shortages of data collection that we've had on the ground during COVID, this is why this particular technology we've seen a significant spike in its use for this purpose of sustainable development monitoring. Overall, our sort of broadest and most general set of observations is that we are interested in moving from the collection of very large-scale data sets to the use of both supervised and unsupervised machine learning techniques to classify and to extract insights and stable patterns from that information set, to the production of what we call big indicators. These are real-time, continuous indicators that tell us about the health and wellness of the planet, on which many other solutions can then be built, which we think of as sort of instruments. That is to say, technology, policy, and finance instruments that are based on those real-time indicators, typically for things that have not been well measured before, that are continuously replenished through the sort of information and insight layer. The analytics and AI layer here is really in the insights layer. Planet's producing lots of information. We're doing some work in insights, but we see the AI community that's represented here as being the principal users of these tools for that purpose. Let me give you just an example of the kinds of things you see through these instruments. So what I'll show you here are, this is a picture of deforestation in the Amazon. We've taken a phenomena at very large scale and that operates outside the normal speed and cadence of human perception and sped it up so that you can see it happening. If you look on the right-hand side of the screen, you'll actually watch the path. This is illegal deforestation happening deep in the Amazon. But what's particularly interesting about this is what you might not have noticed while you were paying attention to what's happening on the right, and that's what's happening on the left. After this round of deforestation occurs here, you'll see on the left these spider tendrils that begin to appear. Those are the illegal roads that appear before the next round of deforestation is due to occur. And if you can reliably use these tools of computer vision and supervised learning to identify where roads are emerging, you can see the pre-indicator of change just before it occurs. And what we're finding is that global law enforcement and governmental policy institutions are now using these tools around the world, but in places, especially places like Brazil, for instance, to do exactly that, to use this combination of data and AI to find the pre-indicators of illicit behavior that attack the integrity of an ecological system and stop the behavior just as it's about to be undertaken. Now, the other thing I wanted to share with you, I thought this is really kind of amazing, is that sometimes the data is not just used to identify sources of infraction or behavior that we want to stop, but sometimes it's used in real time to tell us about the health and appropriateness and success of various approaches. I want to show you here, this is an illustration of the path of deforestation around an indigenous land trust in Brazil. So what you'll see here, this includes some data from Planet and some from other sources. I'll just run the animation again, but you should get the general idea. In this case, where indigenous people were given authority over the land, they were able to protect it otherwise from the path of rampant deforestation, which otherwise characterized the work activity in the area. Now, the next way in which we're using supervised learning techniques today is in the combination of multiple data sets to produce essential indicators for what we call essential planetary variables. On the left here, you'll see planet imagery, just like that example that I used a moment ago of deforestation in the Amazon. And what we're doing is combining that optical imagery with airborne LiDAR data. This is LiDAR, as you may know, is a volumetric data source. It tells us about the three-dimensional structure of objects. In this case, we fly an airplane over the forest canopy and we get long strips of LiDAR data that tell us about the three-dimensional structure, which we can then use in a supervised learning technique to combine with and then extrapolate where we don't have the LiDAR data, but we do have the optical imagery. And the reason that's important is where we find correlations and then extrapolate between the LiDAR data and the optical data is that when you start with LiDAR data, from LiDAR data, you can get biomass, and from biomass, you can get carbon. And because we can then extrapolate in the other direction from the LiDAR data plus the satellite data, the optical imagery for an entire region, what we can then do is produce a three-dimensional volumetric map of, in this case, forest carbon. And what you see on the right here is actually a map of carbon density for an entire country, in this case, the country of Peru. Because we are then operating these satellites on a daily basis and we are capturing the whole country every day, we can actually produce a real-time indicator of forest carbon that changes on a daily basis.
Might have lost Andrew for a moment.
Oh, sorry, can you all hear me? Sanjay?
Yes, we can hear you.
Oh, good. Okay,
I
sorry.
can hear you.
It sounded like someone said they lost me for a moment. So in this case, what we're producing is a...
Hi, Andrew, can you hear us?
Indeed, I can.
Yes. Yeah.
Okay.
Yeah, but
Yes.
the
Yes.
sound
Yes.
is okay.
Okay. Great. Excellent. So this is important because protecting terrestrial carbon is an essential strategy for ensuring that we reduce and reverse the process of climate change. Storing carbon in the forests is absolutely essential. And we're using exactly that technique actually in a couple of places around the world. We've just started to do it for the entire state of California. What you're looking at here is something called the California Forest Observatory. Here we don't care about the carbon as much for its climate change potential, but for its potential risk of forest fire, climate exacerbated forest fire. Because the size of a typical tree crown is larger than the size of a pixel, what you're looking at here are individual trees captured in the satellite imagery. And this monitoring system allows us to make much more calibrated models of forest fire risk, and allows us to take much more efficient mitigation actions. And that's in fact what's happening right now. In fact, those techniques are so successful that we've recently partnered with the government of Norway and the entire United Nations Food and Agriculture Organization to take all of the forest data we collect between 30 degrees north and 30 degrees south for 64 countries and make them available as a digital public good so that we can accelerate actions that are intended to arrest or reverse processes of deforestation. Other examples within the Sustainable Development Goals, just to give you a few, one of them is this effort called the Allen Coral Atlas, which you can visit at allencoralatlas.org. This is a comprehensive effort funded by an organization called Vulcan, involving Planet and a host of academic research institutions. These are combinations of machine learning and conservation science teams at Arizona State University and at the University of Queensland. And what we're doing is taking all of the data that we collect about coral reefs worldwide and a series of consistent methodologies for ground truth collection and producing the highest resolution classified maps for all of the world's coral reefs and making them available as a digital public good, and then building real-time monitoring systems on top of them. Again, what we like to do is take these, the reason that this is actually interesting, I should say, is because coral reefs are the canary in the coal mine of climate change. They're a little bit like underwater forests. They're immovable, they're highly sensitive to temperature fluctuations and changes in ocean heat and acidity. And in fact, that's a signature effect of climate change. So we're working on ways of improving applied conservation science using this combination of machine learning and real-time global data. In fact, actually, that data is having real-world impacts. Just at the beginning of last year, we started to see the first new marine protected areas written into law, in this case in Eastern Sri Lanka, using that data as a principal source for justifying their conservation, because we can actually see the biodiversity from space that's happening on the reefs. Another example also has become incredibly important during the period of COVID is in food security. And here we have a massive partnership with our colleagues at NASA, specifically a program called NASA Harvest, which is working on real-time crop analytics, specifically for crop estimation and for yield estimation. Here, working in Togo, looking at the impacts of COVID on agricultural yield and agricultural yield forecast, looking at where potential food insecurity might occur. And of course, these tools are relevant in an applied way for dealing with COVID itself. We are fortunate to see the advent of new vaccines, but the distribution of those vaccines is something that's going to require monumental effort. Here we're working with a group of spatial epidemiologists, an organization called ACROS, another one called Locational, using these tools to determine where all of the residential buildings are and where human settlements are, in particular in less well-connected, more rural populations, and overlaying spatial epidemiological models on top of them to determine which of those residences and which of those communities need prioritization for delivery of the vaccine. The thing that's particularly exciting about this, and I wanted to harken back to something that was said earlier, which is about the feedback loop. It's not just about data, algorithms and models. It's about all of the complexity and high dimensionality that's happening in the world. And one of the ways in which we get at this is just by observing the world on a daily cadence, doing the whole world every day. What that enables is a certain kind of feedback loop in which we are, in this case, building models driven by satellite imagery and spatial analytics that drive the behavior of public health workers in the field who are doing vaccinations using this data. And then as they collect more field information in the context of that behavior, feeding that back into the models that allows us to increase the specificity, increase the accuracy, and find the next places where human beings need to go. The other thing that these tools are useful for producing is analytics that wouldn't be available any other way. Here I'll mention, this is particularly related to climate change. It is unusual for coal-fired power plants around the world to actually report their behavior and performance, and they're highly variable sources of energy production. They can be turned on and turned off with little or no notice, and it's very hard to get information about their overall activity. We work with an organization called Carbon Tracker that uses standardized computer vision techniques to monitor coal-fired power plants, watching not just their smokestacks, but also looking at the volumes of coal piles that are fed through these systems, through these plants, and assign rigorous emissions factors to that behavior such that we can get aggregate information about emissions from coal-fired power plants that would not be available literally any other way. And in principle, they've shown that they can do this activity with the data on a global basis around the world. We haven't gotten there yet, but we're well on our way. The last example, the last two examples I'll give you, and then I'm happy to close. Sorry, I'm getting a little bit of feedback. Is how we use these to identify climate-related risk in environments where it's otherwise very difficult to get it. And this is one of those examples where I see there's a tremendous opportunity for us to scale these activities. So what we do is, as I mentioned, we take this daily global satellite imagery. And as I mentioned, we use some supervised learning techniques, principally to extract monthly building maps. So we're producing a map of an area, then we're extracting all of the roads and buildings, as I showed you at the beginning. Then we're overlaying on top of that a hydrological flood risk map. And what you get when you combine those things is an urban risk map that allows you to see where people are moving in or out, where are the building starts and building closures that are happening in places where there might be accelerated risk. Sorry, is anyone else getting some? I can't tell. All right, I'm just going to mute myself. I hope that's okay. So, for example, here's a city in sub-Saharan Africa. This is the city of Bangui in the Central African Republic. It gets relatively little monitoring. It's what we call one of the least. It's in one of the least developed countries, the LDCs. Here it is, roughly a year later. So here you see the shift in the city over that period of time. Here, according to our analytics on a gridded map, is where all of the most intensified building processes occurred. And here is where the hydrological risk map is. And so, for instance, if we look at this area here, we actually see where people are building. There's a significant amount of building activity in a place which is at elevated risk of flooding. And one thing we know about climate-related flooding is that those places that are subject to monsoon seasons, that are subject to rainy seasons, the risk of climate-related flooding is substantially increasing. And again, these are the kinds of analytics that we need to produce new kinds of mitigation activities. Those might include improved flood walls. They might include better flood insurance products. They might include climate-adjusted municipal lending to enable more climate resilience. And that is, in fact, actually how these tools are now being used. The last example I'm going to give you in my remarks today is actually to show you what the measurement of a real SDG indicator looks like using these tools. So this is a system that uses very similar techniques to what I just showed you to look at SDG 11.3.1, which measures the growth in population relative to the growth in the physical size of communities. So we're looking for the ratio of sort of urban density, its population to size. And these happen to be communities in rural Tanzania. So I'm going to show you this is an application we built internally. Here you'll see me moving around. This is some of our satellite imagery zoomed out. I'm going to zoom into a particular community here after turning on the kind of growth and destruction. And what you see here is in blue, those areas in these communities that on an interannual basis have grown. In red, using a standardized algorithm where they have contracted. It should be unsurprising to you that, and I'll just go back for a moment, it should be unsurprising to you that in most of these communities, we've seen just year on year a substantial increase. And the reason for that increase is there's nothing constraining these cities, these communities. So they grow, there isn't particularly some either regulatory or physical boundary condition that keeps them contained. And we can see this level of urban growth on an annual basis. This is the actual measure of the SDG 11.3.1 indicator. And we can see it not just for an individual community, but as you'll see here, and I'll zoom out, we can also see it for the country as a whole. In fact, we're now running these analytics for the entirety of Africa, just on a regular basis. This is just the beginning of these techniques in their applied sense, and I'm delighted to be able to share some of them with you today. I'm going to just stop there. Thank you very much for the time to address you this morning or this evening, and I look forward to taking questions when there's time later in our session. Thanks again very much.
Thank you, Andrew, for this wonderful talk. Yeah, I think we'll take questions in the end.
Stop sharing my screen.
There are a few questions. I guess one I think maybe you could answer now about taking so many because of the data you're collecting. Do you worry about privacy concerns from satellite imagery or?
Sanjay, I appreciate the question. I believe you asked about privacy concerns. We selected our mission parameters primarily to avoid the issue of personally identifiable information. We're not, a typical pixel in these images is about 3 meters on a side. So no one's reading anyone's newspaper or spying on anyone from space. There is no question, however, that the combination of data sets, particularly mobility data and satellite data, does have significant power, particularly to produce demographically identifiable information about populations. We are very careful and have a very active ethics program that looks at these use cases and ways in which we can ensure the continued utility and value of the data without causing undue privacy considerations. It's worth noting that, broadly speaking, the satellites that zoom in at the level where they might really violate your privacy are principally reserved for national security considerations. We don't make those kinds of satellites for that reason.
Yeah, great. Thank you. There's some more questions, but we'll ask them at the question and answer session. So thank you for your time. Thank you very much. So David, do you want to share your slides now? David, are you there? Let's see. Oh, there he is.
I'm sorry. usual minor distractions of life. Do I share or?
Yes, please share your slides. Thank you.
There we go.
So once you share them, I'll quickly introduce you. And
here we go.
Okay,
that
great.
should show. And here we go.
So quickly, thank you very much, David, for giving a talk at MLDAS. So David Forsyth is a professor of computer science at the University of Illinois at Urbana-Champaign. He's known very well for his work in computer vision, and he's also the author of a very famous textbook called Computer Vision, A Modern Approach. And there's a connection with QCRI, and he's Amin Sadeghi's advisor whose talk is after David. So David, over to you.
Thank you. Thank you for the kind introduction. Firstly, I hope everybody can hear me and see the slide.
Yes.
We're good. Thank you. So I'm going to talk about shadows and shading. I was delighted by Andrew's talk, but I'm going to talk about a sort of gritty, detailed aspect of computer vision rather than this beautiful big picture of how you can use the understanding of pictures to enhance humanity's experience and quality of life. And I'm going to talk about a very minor gritty issue. But before I do this, I do want to introduce my colleagues and just sort of generally say hello. We have a large and active computer vision group at the University of Illinois. I'm sort of the necessary famous old guy, but we have my younger colleagues, Derek Hoyam, Lana Lazebnik, and Alex Schwing, all of whom are busy getting famous. Saurabh Gupta, Lina Gui, Shenlong Wang, and Yuzhong Wang, who are recent hires. So it's a very active community. Computer vision is a flourishing discipline. It's very strong and very effective. There are things that we're just really good at. It's truly wonderful to see that a whole bunch of satellite imaging problems are solved. Ooh, I'm hearing myself. Somebody's got.
It's coming
We're
over.
getting an echo. Let me try again.
Okay.
I'm still getting an echo.
David, this is Andrew. I'm also getting an echo. I found it was helpful to mute or sorry, turn off the volume. It's my own computer.
On your own computer. Maybe that's the issue. Okay. Sorry, we tried this, but this issue didn't arise. Let me deal with that. Right, let's try again. I will ask if anybody could hear me, but then I can't hear your answer. So perhaps somebody could wave on the video or something.
Yes, we'll do that. Thank you.
Wonderful, thank you. So computer vision is really very strong and effective. And what was another really charming feature of Andrew's talk is a whole bunch of problems about satellite imaging that are solved well enough that you can do something useful with them. There are things that we are really good at. The things that we're really good at are using data to construct effective and highly polished visual features, which we can then use to do classification. So is this pixel covered by coral reef or road or something? We can do detection. We can do reconstruction. We can build 3D models of objects from video. But we actually, remain very deep problems. And they're important and interesting. So one very deep problem is what does or should vision do? So we know that computer vision systems accept images, but the question that is genuinely interesting is what should come out? And that turns out to be hard and poorly understood. Another is there are very specific rules about how machine learning works, about how data set bias works and representation, all of which are repeatedly and grossly violated by almost every known computer vision method. and nothing particularly bad goes wrong as a result. It would be nice to know a new set of rules where it wasn't fairly clear that we were doing the wrong thing and that explained why our methods work. We have complex, very poorly understood machinery that mostly behaves very well and allows us to build things we simply couldn't dream about 10 years ago. But at the same time, the machinery, we have no real idea of how it works internally, and it occasionally displays very odd behaviors. Deep networks have all sorts of odd and annoying behaviors, including adversarial examples and the like, which are very poorly understood. So there's another challenge, taming the machinery. And the challenge I want to talk about today, which to my mind is very important, are problems where there really isn't much or any training data at all. So here is why we care or should care about shading. Different pictures of the same thing look different under different lights. This is a set of 6 images from a webcam in Finland. I found them on Flickr. For some reason, people find webcams fascinating, and they show lovely effects. So there is a marine crane here, and what you can see is as the time of day changes, everything looks different. Sometimes the crane is bright yellow, sometimes it's a little bit orange, sometimes it's some dark color which is indistinct because you can't tell. The roadside goes from a fairly light gray-brown color to a very dark gray. And what's going on here is the same stuff is changing appearance because the light has changed. There are important consequences, and they're observed every day by users of vision systems, which is classification doesn't work as well as you'd like it to, and detection doesn't work as well as you'd like it to, because contrast and color have changed. So there are 2 strategies for coping with this effect. One strategy is you might compute a representation of things in the world that is independent of shading and use that representation. Just get rid of the effects of shading and then get on with life. And of course, the big question here is how. The object we're talking about here is known as an intrinsic image, and there's a 50-year line of research into producing them, which still faces serious problems. And we'll talk a bit more about that. Now, the other thing you could do is train a method to ignore these effects by showing it lots and lots of examples of how shading changes pictures. And then, of course, that strategy runs into the problem of how do you do this? Because our current evidence says we haven't got enough examples of that. Why? Because shading causes classification and detection problems. What you might want to do is reshade scenes as a data augmentation process, or insertion render objects into scenes at known locations, so that you can use them as training data for training detectors. And of course, we don't know how to do that either. And I'm going to talk about these 2 problems. So here are the 3 big questions in understanding shading. One is, I would like to be able to do what I like to call insertion rendering. I'll cut an object out of one image, I'll stick it in another image, and when it goes there, something should happen to make it look natural. Now, there are obvious reasons you might want to do this. One is for training detectors, but another is it's just a fantastic rendering paradigm for computational photography. It'll make users on Snapchat happy, etc. The second question is scene reshading. I want to take an image of a scene and generate a new image of that scene, shaded differently, so the light looks as though it's moved, and I want that picture to be natural. So I could do that for training classifiers. I generate a whole bunch of different examples. That gives me data augmentations, and my classifier now is smart about shading, and I'm happy. The other obvious reason to do this is computational photography. And the third thing, of course, is controllable scene reshading. I want to generate a new shading of a scene that looks natural and is like some target. So I really want the light to be on the left. I really want the light to be on the car. I really want the shadow to be off the car. Why would I do that? To train detectors, to train classifiers, and computational photography again. And I'm going to show you some progress on these questions, which remain hard and deep. So there's one standard strategy for attacking these questions. It's known as inverse graphics. You build a really big data set of 3D stuff with surface material details. You render that data set. Then you train a regression, basically a neural network, to reconstruct that stuff from the pictures that you made. And then you reshade scenes by, you take a picture, you apply inverse graphics, and you do a physical rendering. Now, it turns out this doesn't work terribly well. It's unconvincing for a couple of reasons. One is it's really hard to build good big data sets of 3D stuff, and really good material models that explain what things look like remain hard to author and create. And the other, of course, is as an explanation of how people and animals actually understand the world, it's kind of unsatisfactory. It's almost certain that the original proprietor didn't load our heads with big data sets of 3D stuff and a computer graphics device. So the alternative is image-based reshading. What we want to do is use images as data without any supervisory information. And of course, the problem is how, and that's what we'll talk about. So here's the first problem, insertion rendering. I want to take an object out of one image, stick it in another image, and I want it to look very good. So the advantage of being able to do so is I know where it is, so I can do detector training, and it's easy to do. The problem, of course, is it doesn't often work. So the original insertion renderer was due to Jean-François Lalonde and Alyosha Efros back in 2007. And here's one of the pictures it made. It's been the standard question to guess which things have been inserted in the picture. Since the question's been out for 13 years, I'm not going to ask it because you could have looked it up by now. But what happens and what goes wrong is when the object is shaded badly or cast shadows work, or cast shadows don't work, it looks horrid. So the little orange guy in this photograph looks bright orange because he was photographed under a sodium light in a completely different picture, and he's not casting a shadow. And the very dark car looks very dark because it was photographed in a very different light. So if the light doesn't work, the picture looks bad. And of course, that will mean if you use this as a data augmentation method for training a detector, that's going to be a problem as well, because the detector is going to be picking up cues that it will not see in real data. Now, imagine you actually know the geometry and material of the object. So I've got like a computer graphics model. Then we really know how to do this. I started this game with Kevin Kosh back in 2011, but now it's way, as usual, these things get way out of control. And now there are really, really good methods for estimating illumination in a single image. And here's a list from a course I've been giving. And even back 9 years ago, you could do a really good job. So you get a picture like this. I've got a computer graphics model of a statue. I stick it into the picture, and it really looks like it's there. Right? The problem, of course, is what we really want is something different, which is I've got a picture of a scene, and I've got something that I want to stick into the scene. In this case, it's a little white sphere. And of course, a little white sphere looks like a white circle. And I stick it into the scene, and then something should happen, and I should get natural pictures that come out. And of course, what is that something? And it turns out that to think sensibly about this, you have to ask the following question. What changes when an object moves from one image to another, and what doesn't? And of course, when I take an object from one image and move it into another image, the albedo does not change, but the shading does. So we refer to albedo as intrinsic. It's a property of the object. It's got, it affects the way it looks in an image, but it's unchanged by viewing circumstances. But the shading is extrinsic. It's changed by viewing circumstances. This is a really traditional vision problem. I give you a picture, you tell me, you decompose it into two. One piece is the albedo, the other is the shading. And you've got to do that without necessarily having any ground truth. Right? And it turns out you can learn very well without ground truths. State-of-the-art intrinsic image decompositions without training data are now really very good. Imagine you could do that. Then here is how you could do insertion rendering. You take an input image, you place the object, so in this case it's a red car with weird doors, into that image, and then you have a mask telling some rendering method where that object is. Then you stick it into a renderer, and that renderer is going to be a learned neural network. And it's going to make me an image. And what I want that image to do is pass several tests. So one test is this like an image? And I'll use an adversarial loss to impose that. Another test is, if I take that image and I compute its albedo, does the albedo look like the cut and paste albedo? Meaning, if I stick a red car into the image, the car is still red, or rather its albedo is still red. Then I will compute the shading of that image, and I'll ask, does the shading field look like a real shading field? And I can use an adversary for that as well. Imagine I could do that. Then I could train the renderer by basically smacking it every time it made an image that didn't look like a real image, and every time it made an albedo that didn't look like cut and paste. Eventually it will learn, and it will make me real images and get the cut and paste albedo right. The problem here, of course, is I need to be able to make the albedo and the shading. And that is tough, because I need to learn to do this without ever knowing the right answer. There are no ground truth decompositions. Rendering is doable but hard, but modeling is hopeless. There is a significant literature on learning intrinsic image methods using computer graphics, and a summary of the literature is you can get tolerable results, but if you want to get decent results, you need to get real data in there somewhere. So how do we know an image? How do we train a decomposition method when we don't know the right answer? And the answer was provided now 70 years ago by Edwin Land with, well, 60 years ago, sorry, with a method known as Retinax. And the argument basically says albedo changes either quickly or not at all. So you can think about the world as being made up of flat pieces of colored paper. When you go from piece of paper to piece of paper, the albedo changes, but otherwise it doesn't. The color of light changes slowly, and there is a family of algorithms that by walking along a path, accumulating changes, can determine what the color at a particular point is. That family is known as Retinax. Turns out it's quite hard to analyze. It's not absolutely clear what it did for about 30 years, but it turns out to be a very effective algorithm. And the particularly neat feature of the algorithm is it's not trained with ground truth data. Now you can modify this algorithm, and you do it in the following way. I'm going to build a traditional UNet with all modern conveniences like skip connections. Into that network will go an image, and I want it to make me an albedo and a shading. And what I'm going to do is I'm going to write down spatial statistical models of albedo and shading. And these models are going to be like Edwin Land's models. They'll say albedo is piecewise constant colored papers. Shading are these smooth changes, but they occasionally change fast. And then I'll multiply them together, and that gives me an image. Now, the paradigms capture, some good stuff, but they're pretty obviously not real images. Anyhow, I'm going to feed those into my network, and I'm going to require that when it gets the product of albedo and shading, it should make the albedo paradigm, and it should make the shading paradigm, and that should explain the incoming image. Now, of course, if I do that, when I give it a real image, it's going to behave badly because it's never seen a real image. So I need to be able to make it behave well on real images as well. And the way I do that is I say, look, if I have a real image, then the albedo that you make should locally look like a paradigm albedo. So it should be piecewise constant. And the shading should locally look like paradigm shading. And the two together should explain the image. Now, how are we going to do that? Well, there's this wonderful trick known as adversarial learning. I write another little neural network that looks at the produced albedo image at the paradigm and tries to distinguish between the two. And if it can, it complains and changes the generator. It wants the generator to make things that it cannot tell apart from the paradigm. I'll basically adjust the adversary to distinguish between the paradigm and the generator, adjust the network to fool the adversary, and get on with life. This is very like the original GAN idea, but there are some small differences, mostly to do with scale, and because it's a smoother. Now, there's some problems. One is the underlying theory of GANs doesn't apply. The theory is not terribly well understood even now, But whatever that theory is, it doesn't really apply here. You can show that there may not ever be a saddle point. And what that means is stopping training at different times gets you different answers, which is prodigiously annoying. There's another annoying feature. If I take that image and I cut out the top left corner and compute its albedo, and I cut out the bottom right corner and I compute its albedo, so top left is TL, bottom right is BR on the slide, what I expect is where they overlap, I should get the same answer. That's an equivariance property. And it turns out that property doesn't hold either. Networks don't know that they're supposed to do that. So what do? What we're going to do is average like crazy. So I will compute a moving average of model coefficients, and that deals with the fact that when I stop at different times, I get different answers. I will get equivariance to translation by covering the image with many overlapping tiles, recovering albedo and shading for each, and then averaging. And I'll deal with scale and rotation in the same way. Now, this is expensive, but it gets me rather nice results. So averaging really strongly suppresses errors. In the top corner, you can see an image of some cats lurking in a lavatory. Why they do that, I don't know, but it's an image from a standard training set. Next to it, you will see the reported albedo. All those shadows have largely gone away. The walls are actually white. It's really quite a good result. Below, you can see what happens if you don't impose averaging. You get these funny pink bits that turn up all over the place. The averaging suppresses those for reasons we don't need to go into here. It turns out you can evaluate these things. So what you do is you ask people to look at images and tell you for 2 points, which point is lighter. You collect a large number of such judgments. And then you've got a task, which is my program needs to predict the same thing that humans do. Now, there are some issues with this evaluation method. There are all sorts of lively fights in the literature about whether it's a good idea or not, but mostly it's quite good. And this task, the recent history of this task is basically methods that see training data during training do better. But methods that see absolutely no WHDR training data in training actually do moderately well. And my method, this BBA and BBAF, is the current best score by a significant margin. Okay. The current best score, you've got to be careful. This is a rough and ready number that tells me we're doing about the right thing rather than a guarantee that everything's perfect, but it's kind of neat. So if you look at the pictures, you get really rather nice pictures. So I'm showing in the far left column indoor shadows that are just removed by the albedo map. In the middle column, backscatter from subsurface scattering in the surface on the tiles, that's been just removed. The albedo really does remove shading effects, and shading things are natural. So we can kind of do this. Is it perfect? No, but it's really very good. And it hasn't ever seen the right answer. There are some problems, and the problems remain difficult. So it turns out methods like this are inclined to rather fudge when they're presented an image with a strong shadow in it. It's an effect that I like to call indecisiveness. You can make it go away, but when you make it go away, the results are weaker, and we don't know why. So if you've got a deep shadow, the method thinks, well, why not put a shadow both in albedo and shading, and then my bets will be hedged. And of course, we don't want that. So here's my finished webcam again. These are the outdoor pictures. I ran into this picture yesterday when I was putting slides together. So the method hasn't been trained on it, hasn't seen it before, whatever. And here's the shading fields that the method predicts. So it really understands that shading changes. You can see that the piece of road heading towards the crane gets darker or lighter. And here are the albedo fields. We haven't gotten rid of the very, very dark shadow, which is annoying. But really what we've done is significantly improve the effects of shading. So that's pleasing. Now, let's go back to insertion rendering. So I said if I could figure out how to build an adversary, which is known, and if I could figure out how to do intrinsic image estimation, then I could do insertion rendering, because I'd basically just smack the renderer until it gave me an image whose albedo was a cut and paste albedo, whose shading was natural, and where the image looked like an image. And it turns out this works, and it works very well. So on this slide, on the left column, you'll see cut and paste, which is what happens if you just cut a white circle out and you stick it into the picture. Basically, it sticks out. There is a method that you could use for insertion rendering. It wasn't intended to be used for it, but you could use it, called image harmonization, which takes a picture and makes it look more natural. If you give it the cut and paste render, you get the center left column, where it certainly looks a little bit more natural, but there's something very odd about the two circular objects. Our method gives the center right column, and you should compare those with real pictures. We went out and photographed spheres in these configurations, and the real pictures are on the far right. So we're now doing insertion rendering that really looks quite a lot like real pictures, and where people often have difficulty telling the difference between pictures and real pictures, our rendered pictures and real pictures. Here are some other examples. So on the far left, there's a target scene. In the center left, there's cut and paste. In the center right, there's image harmonization. And in the far right, there's our insertion render. And the car just looks as though it was there. It turns out that the way you compute intrinsic images matters. So the best known intrinsic image method is due to Lee and Snavely, or the current best, it may have changed since the CVPR deadline, is the best that we had was due to Lee and Snavely. And if you use that method, you get a better WHDR, but you get a worse insertion rendering. So you really do need to think about how you do intrinsic images, and doing them the way we're doing it works. So I've shown two of our paradigm methods. Method 1 is much better than method 2. And the Lee and Snavely method, it does better on WHDR, but it's not good for insertion rendering. There's another rather neat feature. If you looked closely at my inserted spheres, the interesting thing about them is the shading on them actually looks like the shading on spheres. Now, there's no particular reason this should be true, right? All I've required is the picture looks like a real picture and the shading field looks like a real shading field. But one way that the network might achieve that is by saying, well, when I see this albedo, I'm going to assume that it has this shape, and then I'll shade that shape. And what we can do is test, does that actually occur? And the way you test is you take some of these spheres, you use a reconstruction procedure to figure out what shape is implied by the shading, and then you say, if I shade that shape, does it look like the other spheres? And the short answer is it does. So there is moderate evidence. You can see in the right-hand side of the slide a surface reconstructed from 7 spheres. There's moderate evidence that it really thinks these things actually should be spheres or something very like it. And then there is a scatter plot on the far right, or a box plot on the far right of consistency, which tells me that if I reconstruct and then shade like other images, the thing is shading it as though it was this reconstruction. So there's considerable evidence that this network has decided, well, you need to think about shape. I'm going to do that all on my own without training data, and it's come up with a sensible answer. Okay, so now how would we reshade scenes? Remember, we want to do this because we want to be able to show pictures of the same scene in different lights so that we can train our classifiers. So a fairly obvious thing that we could do is take the albedo, multiply it by the desired shading, and get on with life. Easy, right? Well, you could do that, but oh dear, this was supposed to start automatically, but it didn't. The problem is, if you do that, they look really unrealistic. So you get these kind of flat, icky scenes. So that can't be right. Why? Well, the answer is shading is very highly correlated to albedo. So if you look at these two crops from that Finnish webcam scene, you will notice that on the body of the crane, in the one picture, the body of the crane is bright. In the other picture, it's dark. And that's because of cast shadow. But what's happening is, because there are surfaces in the world, the shadow is cast onto the body of the crane in the right-hand picture, but not onto the ground because of the positioning of the light. So when I move from the body of the crane to the ground, the shading field itself changes, as does the albedo. And what that means is even when the decomposition is correct, shading is very highly correlated to albedo. And below in probability talk, the probability of shading conditioned on albedo is not the same as the probability of a shading field. The conditional distribution really matters. So the way we want to think about this is when I reshade a scene, I'm actually drawing a sample from some model of the probability of shading conditioned on albedo. The difficulty is I want to learn this model from many of my decompositions, but I never really see one scene in two shadings. Now, this is really hard to do. It turns out there is a long literature on building these conditional models in vision, and it's all a little bit shaky. Here's the kind of thing that happens. So let's see, the bottom movie, middle movie, top movie, all the movies are, we'll rerun the movies. On the left is the true shading field, or rather is a controlled shading field. On the right is the demand. The reason that we get better controlled shading fields is we know that the background, or the shading of the background, we know what the surface shading correlated effects are in the background. So I demand the right, and I get the left, which is much more complex and gives me a more interesting and effective scene. So here are controlled reshades. You can see the little lights flying around the world, pointing out bits and pieces, and you can see they cast local shadows, which is what they should be doing. You can also see the real appearance of shape, which had been flattened out in the earlier movies. But it is very difficult to draw conditional samples or to build a conditional model that gives you diverse samples. So I showed you the movies because those movies show controlled shading demands. And the nice thing about a controlled shading demand is I can force the thing to make a bright light in the top left-hand corner and a natural shading field with that. But imagine I just draw a sample from the conditional distribution. The problem I'm going to have is with current methods, that sample tends to be like the last sample. And mostly it isn't absolutely certain why this is the case. There are a variety of difficulties in training the conditional models. But what you see over here is 10 conditional samples each of shading fields for the same scene. And the important take-home message here is they're all about the same. It is fantastically difficult to get them this different. This is about state-of-the-art for diverse colorization. But now this is diverse shading, and nobody's done diverse shading except me, so this has to be state-of-the-art. But they really are pretty similar. Why is diversity tricky? It turns out it's hard to force samples to spread out, and current tools really don't know how to do it. So the early stuff, the image-to-image translation stuff, just doesn't impose a diversity requirement. In more recent tools, there are some methods for imposing diversity requirements, but they're really, as we saw, just not that good. We need to make these tools better. However, recent work by a very able student of mine, Minjin Chong, has demonstrated extreme diversity in another context. And I want to show this to you because it's a nice bit of fun and we're almost finished. The aim of the method is the following. I want to turn a face into a cartoon. Now, if you're dedicated to shading, think about this as turning an albedo into a shading field. But I've got face and cartoon working, so the expression needs to be controlled by the face, but the style of the picture needs to be controlled by a random number, or rather a random vector. And the reason I want to do that is I want to be able to change the style of the cartoon. And you can see here, this model, I think this is from TikTok, but it's one of these videos that goes around. I'll show you the video and the like. This is a frame. And you can see here, she's been turned into a manga, and the manga is coherent. It looks like a really, an artist-drawn manga, and her hair color has a particular color. The eyes are coherent. They have a particular shape. Left eye and right eye have the same shape, which is hard to achieve and the like. So in coming work, what we're going to do is take this extreme diversity machinery, which I haven't described in detail, take this extreme diversity machinery and drop it on shading from albedo. So here were my key points. Vision is flourishing. Vision's just great. It's a really, really exciting discipline at an exciting time. Old problems are deep and they matter. So shading in intrinsic images as a vision problem has been around since about 1959. And the issue really, really matters still. There are many applications. One can recover other kinds of intrinsic image. So an image that tells you how bumpy surfaces are, how smooth, how slippery, how bouncy, that kind of thing. We're doing albedo and shading, but there are others. And the final point is you can actually learn very well without ground truth. So I've shown you state-of-the-art intrinsic image decompositions without any training data. I've shown you state-of-the-art reshades without any training data. And I've shown you state-of-the-art scene reshades without any training data. Now, the third one is a bit of a cheat because nobody else is doing it. So, you know, if you're the first guy on the scene, then you're state-of-the-art a fortiori. And I've also shown you significantly promising diversity tools. I'm going to show you one neat feature of these diversity tools, which is they make movies for free. So the face I showed you in the previous slide, what we could do is make a movie of turning her into a manga just by taking each frame separately and turning it into a manga. And then when the beat of the music occurs, which is why I'm going to force you to listen to what is frankly rather ghastly music, when the beat of the music occurs, we're going to change the style of her face and it's going to work. So the next big step is dropping all this neat new machinery on albedo and shading. So let's move on. Here we go. Here's extreme diversity in movie form. For some reason, it seems like you can't hear her. It's on the whole, it's a grace, but what you do need to know is every time the beat changes, her hair color changes. So the beat is when the hair color changes. And what you should notice is how clean and consistent and diverse the styles are. That's me for the day, pretty much dead on time. And I guess we'll move to questions or discussion. Or
thank you, David. We'll take more questions in the question and answer session.
Oh, I better turn my sound up. Otherwise, I won't hear any questions or discussion. I'm with you in a second. Sorry. Here we go.
So I was just mentioning that we'll take some questions at the end of the session. But I think there's one question from Dragos about Dragos. Do you want to ask a question or?
Yeah, no, fascinating. I mean, the fact that you have a probabilistic model for albedo and shading, right? And you generate these fantastic scenes and so on. And we know that this is growing. I mean, we start to have probabilistic models for generating movement and so on. Can you talk a little bit about the state of about the state of the art in this? No ground truth data because we can't afford it, but we build these probabilistic models about functions of the images, and we generate realistic scenes, images, and so on.
I can go on for hours on the topic. I think it's the great new frontier in vision. So for 5 years or so, the adversarial trick was sort of seen as a way to generate images, but there wasn't really much understanding of why you would generate images. The literature of the last couple of years has been developing the point that if you really know the difference between a real image and a fake image, you know an awful lot of stuff that isn't obvious. So we know now, for example, that if you have a face generator that can really tell the difference between a procedure that can really tell the difference between real and fake faces, you can recover shape easily. And the way you recover shape is essentially you pretend you have a face model. Then you take a face image, you move that image onto the 3D face model that you have, then you generate an image of that from a slightly different point of view. And if that image isn't absolutely realistic, you've got the shape wrong. And it turns out that procedure allows you to produce really, really good shape models without any ground truth data. All you need to know is the difference between a realistic image and a really bad fake. Right? The evidence, I think, is you can probably do most of the traditional inference procedures of computer vision using that argument. Right? I'll do a reconstruction. I will render that reconstruction, and if the image that results is not realistic, then my reconstruction was wrong.
Yeah.
And if that is true, it means that we basically just don't need ground truth data.
Yep.
Okay, great. Okay, thank you, David. Thank you very much. Amin, you want to share your slides before I introduce you?
Yes, I think you need to pass it on to me. Hi, David. Thank you very much. I enjoyed talking to you.
Nice to see you.
Nice to see you. Thank you. Thank you.
Okay, now you're on.
Okay, great. Okay.
So quickly, Amin, let me introduce you. So
Sure.
Amin Sadeghi is a scientist at Qatar Computing Research Institute. He joined us in January 2020, just before the pandemic. So we managed to get him before that. And he did his PhD from UIUC with David. And before coming to QCRI, he was a professor at the University of Tehran. So over to you, Amin.
Thank you so much, Sanjay. So I was very delighted, and I'm very fortunate to have had completed my PhD under David Forsyth. It was a wonderful opportunity. And now also at QCRI, I think I am very delighted to work with wonderful people like Sanjay and other scientists. So we have been working on a general problem of analyzing satellite imagery and analyzing roadmaps and things like that. And it has been an ongoing project since like 5-6 years ago. And I have joined this project since about 2 or 3 years ago. And, we have published a lot of interesting papers. We have techniques to generate roadmaps according to satellite imagery. We can detect changes in satellite imagery, especially changes in roadmaps. And there are interactive tools that we developed that basically let you interact with the computer to generate better maps. And then we have techniques to infer road attributes, and we can infer roads basically using GPS trajectories. And also we have like generative adversarial network techniques that can help us improve the quality of extracted roads. And so it has been a wonderful collaboration. But the official collaboration ended about 1 year ago, but we have unofficially continued our collaboration. And the current problem that we are looking into is to be able to estimate the risk of accidents at each location on the map. So if you look at this map, each location has a risk of accident. Like there's this intersection here, which is high risk. There's this road here, which is relatively high risk. And there are these like quiet streets here that are low risk. And the problem is, the problem that we are interested in studying is to be able to predict the risk associated to each location on the map. But the fundamental difficulty is that we are given only a very sparse set of accidents. And in this regard, the problem is similar to what David just explained. We don't have enough ground truth, and we don't want to be, required to need plenty of ground truth. So we have, let's say historically, we are given a bunch of accidents. Each accident has a location and has a timestamp. And what we want to do is to be able to, given these accidents, given these historical accidents, come up with a risk estimate for each location. So this problem is fundamentally complicated because of the underlying sparsity. Since there are few accidents, what people have been doing, basically, some people try to reduce the map resolution so they have more accidents in each cell. So if you look at this image on the right, they use like cells of, let's say, 100 meters by 100 meters, and they count how many accidents happen in each cell. And basically, they call this the underlying rate of accidents. And they basically predict this rate of accidents. There are also some other works that try to blur this out to make a more smooth output. But if you look at these images don't give you a high resolution. And having a high resolution is very helpful. You can identify which intersections are the most dangerous. If you want to design the layout of some road, basically, if you want to design some road, you can try to, compare different designs and figure out which one is the least dangerous design. So there are a lot of different applications. But the fundamental problem is, there is an underlying rate of accidents map, and the kind of the accident that you observe at any given year is just a Monte Carlo sampling of this underlying risk. So it might be the case that there could be a very high risk place, for example, this intersection here, but just by chance, it's possible that you don't observe any accidents at this location. But there is also the other possibility where there could be a very quiet place and safe place, but again, just by chance, you can observe some accidents, right? So if you want to figure out the underlying risk of accident at every location, relying on the historical frequency of accidents is not going to give you the best results. It's going to basically be impacted by some sampling noise. So, some people have tried to reduce the resolution in order to combat this, because if you reduce the resolution, the variance decreases, and that's how you can control the output. But some other people have tried to use blurring techniques on the historical data, which they call kernel density estimation, which is basically you just look at what places have experienced accidents in the past, and you just try to blur it out so that if the next accident happens very nearby or very close, somehow you can capture it. And this is basically, these two categories are the categories of works that people have been doing on this. And, there is, prior to this work, there was really no high quality accident risk map. And we were the first work to generate high quality accident risk map, which is this. If you look at the image on the right, you can see that we have been able to identify that there are some, like these intersections are more dangerous than these streets. And there are some streets and valleys that are less dangerous. Some are more dangerous. There is this street that is apparently dangerous, but you cannot see these patterns here in the kernel density estimation techniques and also in low resolution map generation techniques. So we used a very simple but effective trick to be able to improve map resolution. And the idea is simple. The idea is if there are two similar locations far away in the map, if they really look similar, they should also have similar risk of accident, right? So like if they have, like look at these two intersections. Both have similar streets with similar widths, both have sidewalks, and basically they look similar, right? So if you observe one accident at one of these intersections and you don't observe an accident on the second intersection, you should still be able to say that the accident at the first location should impact your estimate of the risk for the second intersection as well. So basically you can share some information between similar locations. So you can use satellite imagery to share this information and identify similar places. You can also use other sources of data, for example, GPS trajectories. Like these are GPS trajectories. You can turn GPS trajectories into like histograms or a bunch of other different kinds of representations. So this is one kind of one representation of histograms, and here we are showing histograms of GPS trajectories along different angles. And so basically, if two different locations on the map share similar GPS trajectory patterns, again, they should somehow share some risk, basically. And we use this trick to improve the technique, and it's actually quite effective. Another source of useful information is road topology, where again, if two different places share similar road topologies, it means that they should somehow have similar risks. So basically they can share information. But prior work fundamentally ignores this, and basically if they share information, it's primarily by looking at like nearby pixels. So basically information is shared only with nearby locations. So basically the overview is we input roadmap segmentation, which is the topology of roadmap. We also input satellite imagery and also GPS trajectories, and also historical accidents. And according to all of these different four different data modalities, we predict some kind of accident risk map. And as you can see in this image, in the future accidents, I mean, in the future, like in the next 2 years of future, 4 accidents have happened at these.
Hi, Amin. I think we can't hear you. Can you hear us? Oops. Sorry about this.
It has an area of about 8,000 square kilometers. So it's a huge area, and we have plenty of satellite imageries, GPS trajectories, and roadmap data. And that's how we run this model and try to predict the accident map. And so this is some, can you hear me? Oh,
Now we lost you for a few seconds. That's okay.
oh,
Now we can hear you.
sorry. So yeah, so I said, I said this deep model, the role of this deep model is to be able to input different data modalities and combine them properly. And we use some tricks to basically get this working. So these are some results from 4 different cities. And the first column shows rough Kernel city estimation, the blurring thing that I discussed. And as you can see, the way it works is it looks at where in this grid of roads you have had accidents, and it tries to basically highlight those places. But our technique not just highlights those places, but also highlights many other intersections and other roads. And if you look at the accidents, there is fair accidents and historical accidents. And the interesting thing is our prediction is more similar to future accidents than the historical accidents. So like these historical, if you look at these historical accidents, it's somehow a random sampling from these different intersections. It means that these different intersections have somehow similar risks, but for some reason, some random reason, some of these intersections have experienced accidents and some of them haven't. But then this pattern is a different random sample in the future accidents. So can you guys hear me properly?
Yeah, we can hear you. Thank you. I mean, we can hear you.
Hello, can you guys hear me?
Yeah, we can hear you. You can't hear us?
Hello?
Yeah, we hear you, unfortunately. Yeah.
Amin.
Yeah. I mean, can you hear us? Oh, sorry. No, okay. No, we can't hear. Okay, I can put you from the speaker here. You can speak from here.
Actually, I was not. Angie, can you make me speaker?
Let me just check. Can you try, sorry, joining again? So maybe you want to share your slides again?
Okay, great.
I think I'm back.
Okay, now you're back.
Okay, good. Okay, so sorry, I just got disconnected for a few minutes. So can you make me presenter so I can share my screen? Oh, okay. So let's share again. Google Chrome share. Okay. So going back, okay, so I think you guys can hear me now. So these are the results for 4 different cities, four different metropolitan areas. And the first column shows the result of kernel density estimation, where they just take historical accidents and just blur the locations so they can capture nearby locations. But our result is much better and it's much closer to the future accidents. We evaluate our model using accidents that occur in future, and basically we outperform other techniques. Another interesting thing is we have 2 different versions of the model. In one version of the model, we don't use any historical accident data, which is this column, the second column. And there is this other version of the model that makes use of historical data. And of course, when we make use of historical accident data, we get better results. But our model is still capable of predicting, accident maps without history as well, which has some interesting applications. So a very fundamental question is, if we don't have the underlying accident risk map as ground truth, how are we going to evaluate our map? So let's say I give you this map and I say this is a good map. How are you going to evaluate whether this map is really, an accurate map of the underlying risk of accidents or not? This is a tough question, because if you traditionally in computer vision and machine learning, if you want to evaluate something, you compare it against ground truth, right? That's how people used to do this. But in these new self-supervised and low supervised techniques, sometimes accurate ground truth is not available. So the question is, how are we going to evaluate whether this is a good map or if this is better than any of the other historical works or not? Because if we output this rate of accidents, this is the accidents that happen in the next following years. Let's say 2 years follow up after we produce our map. So it's not easy to evaluate this risk map using these individual accidents that occur, right? So it's not obvious. There are multiple ways to do this. One way is to say, to assign positive labels to these pixels, to these red pixels, and assign negative labels to other pixels, and try to come up with some precision recall curves. And basically, it's easy to show that our model with different kinds of data that we input outperforms prior work. And and the more data that we use, the better. For example, if we use GPS trajectories and satellite imagery, it's better than just using satellite imagery. And if we just use satellite imagery, it's better than just using just roadmap. So basically, these new sources of information help us come up with better predictions. But also, it's also clear that historical accidents also help predicting better results. The left precision recall curves are the setting with 2 years of historical data, where 2 years of historical data is supplied to the accident prediction model. But the right precision recall curves are for the setting where we don't have any historical data given to the model. And it's clear that if you supply historical data, the model performs better. But even if you don't supply historical data, the model does a pretty good job. But the thing is, there is an upper bound here because the ground truth that we use to evaluate our model is not the true ground truth. It's a proxy to the ground truth, to the true ground truth, because the true ground truth is the underlying risk, which is not given. So instead, we use a proxy, which is the accidents that happen in future. So then there should be an upper bound here to the average precision, the maximum average precision that you can get. But there's a trick that you can find an upper bound and somehow remove the effect of the ground truth noise or ground truth inaccuracy. Because as I said, our fundamental ground truth must be the underlying risk of accident, but that's not given. So we need to resort to using just future accidents. But there is this cool trick that we can use. Assume H is a vector that each element of the vector measures the historical rate of accidents at some location. F is also a vector of the same size, but it measures the rate of accidents in the follow-up years. So it's basically future accident rate. R is the underlying, fundamental underlying rate, which is unknown. And R hat is a prediction, the predicted rate, which is what we predict. The interesting thing is, if you think about the underlying risk, which is this red points at the bottom of the screen, the kind of error you have with the history and the kind of error you have with future are somehow orthogonal. So because history is a sample from this underlying risk, and future is also another sample from this underlying risk, they have two different sources of noise or sources of error, so they are decorrelated. So it means that if you want to, you can measure basically the difference between the history and the underlying risk by just measuring the difference between history rates and future rates, and just basically using a triangle inequality and Pythagorean theorem, and basically say that you can basically calculate that the difference between historical accidents and the underlying rate of accidents is basically square root 2/2 times the difference between historical accidents and future accidents. So basically, this is a way that you can estimate the deviation from historical accidents and future accidents comparing to the underlying risk, even though you don't have the underlying risk. And another interesting thing is you can say the same thing with your prediction, where you can say, so again, if you assume that our goal is to figure out the underlying risk, and our prediction has some error comparing to the underlying risk, and the future accidents have also some error comparing to the underlying risk, these two errors are also decorrelated because they come from two completely different sources and they are decorrelated. So that's why you can again have this assumption that basically this equality basically holds. And making use of both, you can come up with you can estimate basically norm of H minus R and norm of F minus R. And if you have the norm of F minus R, which you can estimate, and if you have the norm of your R hat, your prediction minus F, then you can calculate the norm of your prediction minus the true underlying risk. So it's interesting that even though the true underlying risk is not given, we can measure our deviation from this underlying risk. And we did this, and we came up with this estimate, and it's clear that there are plenty of numbers here, but basically our models with different sources of data outperform prior work with a good margin. So I just, within the next 2-3 minutes of the time, I'm just going to give a quick explanation of what's going on. So basically, we have this bias variance trade-off, where the total error is the sum of our variance error and our bias error. And as you increase model complexity, you increase variance, and you increase total error. If you decrease model complexity, you increase bias. So there is a sweet spot here that people choose. And this is how people optimize their hyperparameters and basically the size of their model. If you think about the two prior techniques that people have been using, low resolution techniques have high bias because they combine the risk of, for example, a dangerous intersection with a quiet road, with a safe road. And so that's how they have they underestimate the risk of the intersection, and they overestimate the risk of the safe road. And the KDE techniques have high variance. And of course, KDE techniques and low-res techniques, they can play with their resolution and their kernel size and basically play with this trade-off. But in general, this is basically what's going on. What we do is we introduce new sources of information that are not directly related. I mean, they are not directly related to accident, but they have predictive power. They can help us distinguish or figure out which places should be similar to which other places and make use of this knowledge. And we fundamentally change this bias and variance curves because we introduce new data to the model. And this is basically a general machine learning explanation of what's going on with our model. So yeah, I'm almost done. If you have a model that is able to predict accident map without supplying historical data, it means that you can somehow use it as a recommender system. If you want to design something, some road, you can just try and compare a number of different designs and basically use it to improve your design. And these are our results, and we have been able to break the state of the art, and we are very excited to have been able to do this. So I'm done with this. If there are any questions, please let me know.
Any questions? I think I mean there'll be questions in the session, the question and answer session. Sure. So great. Anyways, we can move. Julie, thank you for being here. Can you share your screen?
Hello, I'm so happy to be here. I think I need permissions to share my screen. There we go. Okay. Yeah. How is that? Can you see that okay?
Yeah, we can see it.
Wonderful. So hi.
Welcome, Julie Shah, who's a professor of aeronautics and astronomics from the Aeronautics and Astronomics Department at MIT, and also a member of CSAIL. And Julie will talk about intelligent machine teammates. I guess AI augmentation, I guess. Over to you, Julie.
Thank you so much. Thank you for having me. So I'm Julie Shah. I'm a professor at MIT in the Department of Aeronautics and Astronautics, and I lead the interactive robotics group as a part of CSAIL. And I'm an AI researcher and a roboticist, and my lab and I work on developing intelligent machine teammates that people can work with more easily and naturally, more the way we work with other people. And the vision behind my lab's work more generally is to develop AI, robots, and more broadly computing that augments rather than replaces human capability. And I've worked for many years in robotics for manufacturing, a wonderful time out at Boeing before I started on the faculty at MIT. and have developed robots that have deployed to work alongside people to build cars and other systems. And maybe I'll start by giving two real-world successful examples of human-robot collaboration in the wild. So one is in Amazon's warehouses. This is a really excellent example of human-robot collaboration through careful decomposition of the work of each, where the robots maneuver the shelves to the edges of the warehouse, where human pickers pick your item and then prepare to ship it, say for next day delivery. But in these contexts, the humans and robots are working in spaces that are largely physically separate. And on the right, I'm showing a picture of one of the quote unquote inherently safe robots, one of the collaborative robots that are safe enough to remove from cages and place next to a person. So it affords you more flexibility in usage of that system in the footprint in your factory. But in many cases, these systems are working next to people, but they're not working interdependently with people. And so these are systems that I say, coexist rather than collaborate. And so one question is, how much of a barrier or an issue is that for use of these systems? They're parsing out the work in these various ways. And to maybe some statistics to help give a sense. Normally I do this kind of interactively and I ask the crowd, but I'll have to answer my own questions this time. How many industrial robots are in operation around the world today? It's more than 1.8 million, which is approximately the equivalent of the US population of the cities Boston, Pittsburgh, and San Francisco. Now, in contrast, make this US centric, how many robots would you guess are in US homes today? It's 1.8 million industrial robots. So there's actually 30 million robots in US homes today. And those are just things that look like robots, like, for example, the Roomba. So that's not including other like Alexa's series, smart home systems. It's not including sidewalk delivery robots, security guard robots, these strange robots going up and down the aisles of grocery stores now looking for spills. So we do have a lot of robots today, in our everyday environment. But for the most part, it doesn't really feel though we have, this many robots around us. And I'd argue that that's in large part because they're not providing substantial value to us because they really need to be narrowly tasked. They operate in structured environments and essentially under constant human oversight. And so as a result, they're limited in the ways they can integrate as a part of our everyday lives and provide value to us. Now, I think this is a barrier in multiple ways. Integrating these systems more deeply into our everyday lives, interaction with people, in our social context is critically important to making better use of them. But there are also risks, I think, to the success of that possible future if we don't get this integration right. And as one example of those risks, this title here is pulled from the headline of a news article a few years ago. At that time, there were so many startups in San Francisco testing sidewalk delivery robots that actually the city revolted. So the elderly and people with disabilities went to the city and asked, for there to be a stop on this because they felt unsafe on their sidewalks. And actually, at about that time, I was attending a AAAS meeting, and I just overheard someone nearby, from San Francisco, complaining about how unsafe and what a nuisance, so many of these systems are. And it's because, much like, in the industrial sector and the warehousing sector, where these systems, operate separately from people, these systems, even though they're being deployed more broadly on our streets, they still don't understand us. We're nothing but obstacles to these systems. And that surely poses a safety risk, but it imposes overhead and other burdens that are unsustainable as we increase the number of these systems that we interact with on a daily basis. So a Roomba doesn't see you as a person either. It senses you when it bumps into you. But that's okay as long as it's one Roomba occasionally bumping your ankle. But the issue arises when it's not just one robot occasionally, but it's a dozen or many dozens of robots that you intersect with in your apartment building, on your streets, on your sidewalks, through your workplace, and so on. None of which are capable of negotiating shared space and acting in ways that facilitate better integration into society. And so, in response to the complaints from the citizens in San Francisco, ultimately, the deployment of these systems were paused in the most populated areas of the city. And these sidewalk delivery robots were relegated to an industrial sector with almost no people. And then there were ultimately limits placed on the number of these systems that could operate on any city block at a time. So removing these systems from these populated areas, is obviously problematic too, because then we cannot mature and further, hone this technology to be useful to us in the ways that we would hope 30 million robots could be useful to us. So, much of my research is focused on addressing this integration challenge, developing AI models and algorithms that enable these systems to not just be safe enough to work in proximity to people, but to be smart enough to do that as well. And so I've worked for many years in robotics for manufacturing. So I love this domain, and in particular, automotive manufacturing. And the teamwork required to assemble a car is really inspiring. It's like a ballet, and you don't think of all of the different ways people pick up the slack for their teammates when one is running behind and resequencing the work. And so, in automotive, for example, we think of this as one of the most successful industries in deploying industrial robots. But in fact, large portions of the assembly process are still done manually, and that's sort of final assembly. So final assembly can represent half the factory footprint and half the build schedule. And it's not that robots can't do some of this work today. They can do pieces of the work today, but it's often not practical to carve out that work and separate it from the rest of the manual work. And so, we have an integration challenge. We need to make robots that are capable enough and flexible enough to work in proximity to people, to be able to adapt to the disturbances that come with these more uncertain environments characterized by people. And so, my work draws heavily from prior research in human team coordination and team training, and from aviation, from the DoD, from the military side. And so instead of summarizing all of those decades of research in detail for you, I will just sum it up with this older picture of Tom Brady, which I need to retire and replace. But we can sum up all of that literature and ask the question, what does it mean? What is involved in being an outstanding team member, and being an outstanding team leader? And for Tom Brady, they say he sees and he knows. So the key characteristics of an effective human team member is knowing what your partner is thinking, anticipating what they'll do next, and then making fast changes as disruptions occur. And so that's what we work on in my lab. We work on developing AI systems and intelligent robots that are capable of inferring human mental state, of anticipating what a person will do next, and then capable of dynamically planning in response to disturbances or changes in the plan. And we develop these techniques to embed in 3 steps or 3 stages. So also critical to a team working effectively together is that team planning to work effectively together. So think about the emergency response team that's huddled around the conference table, looking at the map together, or the team that's formulating their game plan. And so we work to embed these techniques in human team planning processes. So systems that are able to follow the natural flow and conversation of a human team, each bringing their own different information and expertise and knowledge, versus paradigms where you have automated task planners or schedulers that miss some constraints, suggest a plan that everybody rejects and then ultimately sets the system aside. So these are systems that embed and follow the human team planning process. So now the challenge is that in forming a plan, we don't anticipate all of the possible contingencies or all of the possible outcomes for what will happen. We don't do that in advance. And in fact, we take these plans and we refine them online through our own experience, through our own practice. And so we also develop AI models and algorithms that learn from human observation and human demonstration, and also learn through human robot interaction how to refine these less granular plans into something that's useful in practice. So medical students, they shadow doctors and they take their book knowledge of how things work and how to deliver care, and they refine that through an apprenticeship model. And then lastly, we work on techniques for execution of those plans, specifically dynamic execution of those plans. So it's not enough to know the game plan. To execute it, you need to be able to online track your partner's progress through the plan and further goals, and plan for how you will communicate or provide meaningful actions to help in support of that plan. So what I'll do is I'll give you some brief highlights of my lab's recent work in both the refine category and then the execute category. So I'm going to motivate the work in the refine category from a project from a few years ago now, from around 2016 or so, in which we worked with a Boston area hospital, Beth Israel, to develop intelligent decision support for the resource nurse or the charge nurse on the labor and delivery floor. And so this charge nurse has a really interesting job. So they essentially do the job of an air traffic controller. The job they do is computationally more complex than that of an actual air traffic controller, and they do it without any decision support. So this nurse monitors and takes in all of the information across these LCD screens, as well as the information on the handwritten whiteboard to the right, which tracks the current patient status through labor and assignments to that patient. And she makes a number of decisions. So she decides which nurses are assigned to which patients are assigned to which rooms. She controls aspects of the OR schedule and many other things. And much like an actual air traffic controller, the nurses that grow into this role speak and feel as though they were born to do this job. It's an incredibly demanding and cognitively challenging task. And there's no formal training process to it. So it takes years of apprenticeship, and some can do it and some can't. And so these are very experienced nurses that do this job. Because nothing is codified, it's very hard to train nurses to do this job. And so we looked at developing a novel machine learning model that could learn from observation or demonstration of nurses' decisions throughout the day, and learn the rules or heuristics that nurse employs. And we use that in two ways. One, to develop decision support for the nurse actually doing the job, so the system could make suggestions as to what should happen next. The motivation for that is that by suggesting some of the simpler decisions or tasks, we can free up or offload the nurse's cognitive capacity for doing the other more challenging aspects of their task, where we require their experience, there's ambiguity, that's related to patient outcomes more closely. And then the second motivation for this machine learning technique was to embed or explicitly encode the implicit knowledge that this nurse gains and holds, to be able to embed that in a computer simulation or training paradigm to train up novice nurses into this role. So break free of that one-to-one apprenticeship model. And the way we do this is we translate insights from cognitive science about how we can learn relatively efficiently through pairwise examples. And we developed a novel machine learning model that was able to emulate nurse decision-making quite well in our controlled studies. I'll show you a video of that system in action, and then I'll talk about how this work motivated the more recent work that I'll share next.
What is a good decision? Right, like, and it kind of made me like.
So regularly placing schedule necessary inspection patient nurse narrative and take care of this.
And so that's the information that she's responsible for. We developed two systems, one with a robot and one with computer-based word.
I recommend placing new patients in triage Satellite Imagery.
What is the bad?
A bad decision would be to place a scheduled cesarean section patient in room 14 and have Nurse Kristen take care of her.
No, it's very specific.
Ginger, what's a good decision?
I recommend placing a scheduled section patient in Nurse Kristen take care of her.
I don't know if you played it back, but for me, it was
Ginger, what's a bad decision?
we are not. Wow.
Cesarean section patient and have Nurse take care of her.
I agree.
So in our controlled studies, these were demonstrations on the hospital floor, but we developed a high fidelity simulation environment, conducted controlled studies. We found that nurses and physicians accepted the system's recommendation 90% of the time, which again is an indication that we were able to learn a high quality model. Now, again, the goal is not to replace the nurse here. We cannot fully replace the nurse, but to use this decision support to free up cognitive capacity so that they can focus on the challenging aspects of their job. And it was a very well received system. So, okay. So now, the secret behind this, much like the secret that exists behind the development of many machine learning systems, is that this success relied on me embedding one of my most fantastic PhD students for an entire year on the labor and delivery floor to learn the work context and the features that these nurses used as a part of their decision making. So this technique relies on being able to identify a priori all of the features that someone is using in their decision making, and then can learn quite efficiently and quite effectively in this and other settings. So and you'll never be able to elaborate all of those decision factors in advance. And in fact, in these series of studies, we identified through analysis of the data and through the models we learned that there appeared to be a switching in strategy for management of the labor floor, depending on how busy it was. So, and there's follow-on literature discussing this. So nurses will make different decisions, doctors will make different decisions. There's actually higher C-section rates when the labor floor is busier. So these are things that are very hard to identify in advance, but are crucial to the performance of these systems, and certainly crucial to being able to codify implicit knowledge via observation. So this motivated the next work in this series of works, which is developing new models and algorithms for being able to learn the implicit factors that affect behavior. So we'll know in advance some decision factors that affect behavior, current, progress through labor of the patients, etc. But there will always be some we don't know. And now how can we, much like we want a system to infer a human's mental state, how can we infer or learn those latent decision factors? So we developed a structured computational model. It's structured in a very particular way to support efficient inference, which is that these latent decision factors are mental states of a person. And changes in that mental state of a person will not change the physical observable world. So my personal priorities or preferences won't suddenly make my drink pop across the table, right? I have to take a physical action in the world that I can observe. That's a part of my observable state. But with this particular structure, we can infer these latent states relatively efficiently from limited data. But there's an underlying challenge ultimately, which is that we want to infer the human's held mental state, and we cannot do that from observable data alone. And I'll give you an example of this. So I'm originally from New Jersey, and in New York, the subways go uptown and downtown at the end of the line. The state of the subway switches. But in Boston, the subways go inbound and outbound from some arbitrary point in the center, Park Street. So if I observe the behavior of the subway, my mental model of that behavior, how I label it or describe it to myself, is different, whether I'm from New York or whether I'm in Boston. But the observable behavior of that subway is exactly the same. It goes to the end of the line, turns around, comes back, goes to the end of the line, turns around, and comes back. And in fact, two states are necessary in each state to describe the behavior of the subway. And so, they're equally good and I need some way of a human guiding or providing input so that I can find the right local minima of this loss function, the one that actually corresponds to the human mental model and becomes valuable for prediction and becomes valuable as a medium for communication about behavior. And so we, in addition to the graphical model I presented on the previous slide, we developed a technique called constrained variational inference that takes time series data. So we can't learn, human mental states from time series data alone, but it pairs it with partial labels, if we have it, as well as high-level input from a human expert, things that are easy for a person to provide. So partial policies and partial dynamics. I might not be able to communicate the names of the states of the subway and its switching, but for example, I can communicate when that latent state changes. As the subway moves through Park Street, my conception of the behavior of that subway has switched. In New York, as it moves to the end of the line, my conception of the behavior of that subway has switched. So what we do is we take this high-level input in the form of partial policies, dynamics, as well as partial labels, and we use them, we reformulate them as constraints on the variational inference process to shape that prior and improve the efficiency of inference. And so what we're able to show by employing this constrained variational inference process is that we're able to infer the sort of true underlying model with much less data and with small inputs of this sort of high level input that's relatively easy for a person to provide. So I'll show you some empirical results on a few examples. So one in which we had a person and robot working together to perform a task, where the person holds their own personal priorities or preferences on the order in which they move through the tasks for preparing sandwiches across the table. Some people might move left from right, some people might move right from left, etc. And so we have our known decision factors, which is the position of the person that we can directly observe through our sensing system. And we have this latent decision factor, which is their intent, the intent of the next place or the sequence of place settings that they're going to move through. And then we have our motion primitives. And what we're inferring are both the transition matrix across those latent decision factors, the initial distribution, as well as the policy. So we're learning the human's policy, where a component of this is driven by the dynamics of these latent decision factors. And so the results I'll show were reproduced in other domains too, the simple subway domain I mentioned, as well as another domain in which a car is sort of changing lanes and overtaking another car. And so what we see both in synthetic tasks where we have true ground truth of the underlying latent state, as well as in real experiments with people where we don't have that, but we can compare the action sequence that we observe to the action sequence of the policy inferred and compare the Hamming distance between the two. The trend is the same, both in synthetic and real data, that unsupervised approaches do not infer latent states and their dynamics that align well with the underlying true latent state. If we have a fully supervised data set with full labels, we can do quite well. That's like the best we can do. But fully labeled data sets are very expensive and sometimes very hard to come by. In the hospital case, we could not have had a fully supervised data set because we did not know that, that busyness of the hospital floor impacted nurse decision making. So what we see with our hybrid approach of some supervised data and this high-level input, employing constraint variational inference, we're able to achieve results that are comparable to fully supervised learning, which is exciting. Okay, so that's a little bit about being able to refine our plans and policies through observation and interaction or taking input from a person. And now I'll highlight a little bit of our work pulling that together to enable human-robot collaboration and execution of a task. So what I've just discussed is being able to learn efficiently a human model through observation and some interaction. And we next need a task model. We need a specification of what actually needs to be accomplished. And we bring those two models together to automatically form or generate a robot model in the form of a partially observable Markov decision process. And the robot uses that to plan its actions, produce a policy. And it does this by hedging over the uncertainty of the human's held mental state or latent state while accomplishing the task. And we've elaborated this model to also include a communication component. So the robot is deciding what action it takes next, where it moves to avoid where it anticipates the person will be. And we also fold in, as a part of that action set, communicative actions. So providing its own updates about what it will be doing so the person can use that in the planning. Or if the robot is highly uncertain of what a person will be doing, the robot can explicitly command or direct the person for what to do next. That's a much less efficient coordination strategy, and so it should be used sparing, but it is one of the natural communication strategies we use in human teams. So I'll show you a few examples of this sort of full system in action with the robot using a learned model of the person, reasoning over the uncertainty in the human's mental state, predicting where the person will go next, planning its own actions, and planning its own communications to the person. And the tasks I'll be showing you involve a person and robot doing various like food assembly tasks. Either the robot is handing over materials or it has its own individual task of pouring juice while the person assembles the sandwiches. And in these tasks, we're working with very large state space, 2 × 10⁶, regarding the sort of granular discretization of where the person's hand is in the space. And we're solving this POM-BP online with a planning time of 0.3 seconds. So every 0.3 seconds, the robot is adjusting where it's intending to move next, what next task it's aiming to accomplish, as well as making a decision every 0.3 seconds on whether to communicate. And just to reinforce the importance of learning, we see when we include learning components, rather than working with a handcrafted model, the human and robot perform the task more efficiently, in less time. And in handover tasks, the number of successful handovers is increased. So I'll wrap up by showing you a video of this system in action, where the person and robot are sharing space to prepare sandwiches and pour juice, and the robot's choosing its actions and communications. Okay, and so the robot here will be pouring juice at each of the 4 stations, but the juice is candy, since juice is dangerous with our robots. Liquids are dangerous. And again, the planning is being done online with a planning time of 0.3 seconds. So every 0.3 seconds, the robot.
Hey teammate, let's make some meals. I will pour juice. Please make and wrap the sandwiches. Let's start. Please make the next sandwich at 2.
So the robot was uncertain as to where the person would go. One way to reduce that uncertainty is to explicitly direct the person to move to location 2. Notice the robot does not repeat this communication because it's tracking the person's hand, knows the person is maneuvering, motioning towards 2, and so selects location 1 to pour the juice. In this case, the robot is not communicating because it actually has a strong belief about where the person is going to be maneuvering next, which is to location 1. And with that high confidence, the robot pours juice at location 2.
I am pouring juice at 3.
So in this case, the robot is providing a status update because that should be sufficient for the person to update and choose one of the other stations. The consequences for the robot or the person, choosing, one of the other stations.
I am pouring juice at 4. I am pouring juice at 4.
Is lower. And in that case, the robot repeated the communication again every 0.3 seconds because after the first communication, the person hadn't made any substantial motion to indicate that more certainty about where they would be reaching next. And so that just gives you a sense of how
I finished pouring juice.
How frequently the robot is not communicating, which is also a success of the model. And again, out of this experiment, when the robot is using both joint action and communication planning, the team performs better than if there's no communication, and performs better than when using a handcrafted model, not employing the full power of the POM-DP in selecting communications. And so sort of some of the latest work of my lab of pulling many of these models and techniques together to develop robots that are more capable teammates from the lab out into the world. And I'll leave you with maybe a deeper dive into various aspects of what it'll take to make these systems successful in society, not just from the AI side, but the ways in which we design for humans and set humans up for success in working with these systems. And so this is a book out this past year with my co-author Laura Major, What to Expect When You're Expecting Robots. It's a light read with many stories, drawing from aerospace and aviation, what we know about effective human interaction with FMS and cockpit automation, what about this can translate, and what are the sort of new frontiers as we deploy these systems more broadly into society. Thank you very much.
Thank you very much, Laura. Julie, this was very nice. So, I encourage the audience to ask questions in the Q&A box, and we have, around 30 minutes for question and answers for all the panelists. So, so there was a question from Dragos. How about tasks? I guess this is for Julie. How about tasks in which there are multiple ways of achieving success?
Okay, so there's many ways to dissect even that question. There's multiple ways in which I can address that question. So there's challenges in learning from observation or learning from demonstration when there's multiple ways to complete a task. Policy blending can be problematic, as you can imagine. Just as a simple example, if you kind of blend or average going right around an obstacle to going left around an obstacle, you end up with something that goes through the obstacle. So learning from heterogeneous demonstrations and specifically taking into account expertise level, is an open challenge, but with some really interesting progress by my former student Matthew Gambale, who's faculty at Georgia Tech, as well as others in the field. And then there's also the flexibility that affords you at execution. So the ability to, with flexibility in how you accomplish a task, you can use that in robust execution of the task. So if one team member is held up or one object is missing for some amount of time, the system can use that and flexibly make progress through the task using the other strategies. And our lab does have work with planning under uncertain specifications. That handles that well. Right.
So Julie, just curiosity, what's your experience of using model-free reinforcement learning in your problems? Have you used them or?
You're breaking up a little bit. I think you're asking.
Can you hear me?
Oh, can you repeat the question? Sorry.
Hello.
I think I can hear you now.
I think we lost you
for a moment. Uh-oh.
Sanjay, we can hear you.
Stop my video. Sorry, I'll stop. I think we lost you for a minute, or maybe my connection got lost. I was just curious. Can you hear me now?
Yes. Yeah.
I was just curious about, what's your experience, and you talked about POM-DP. What's your experience about using, reinforcement learning in your problem space? I mean, do you have, generally what's the experience with them? Model-free reinforcement learning, I guess.
Yeah, we've worked within a reinforcement learning context or framework over the years as well. So some of our work is more focused on trying to address the impedance mismatch between sort of training a person to understand the behavior of a system and taking input from that person at a much lower frequency to guide the behavior of the system, and balancing that with a system being able to gain proficiency through many, many more episodes, like tens of thousands or hundreds of thousands of episodes in simulation, maybe even between the human interaction. And the ability to balance that has significant benefits to human robot team performance. So for example, we know we have to train on technology. We all need training to use technology. And when a system is co-learning, while we're also learning the behavior of the system, you have this really interesting problem that arises. And so how do you sort of draw a person along the system's learning curve? So they're building their own model of the system's behavior. And so we've done that in with more model-based approaches. And then model-free RL, we have some work in inverse reinforcement learning. So trying to learn the reward function or the logical specification, which then can be used as a reward in a reinforcement learning context to produce policies. Yes, we do have work in that area. I still to this day struggle to find the real world settings where you have a perfect emulator or simulator to train your system up in. And so I'm always looking. So we to find, we have fewer real world applications in that setting because of that.
That's good. Thank you. Thank you. So, you know, while I'm hoping some people will ask questions, so maybe I'll ask, you know, Andrew and David, you know, we always talk about the satellite imagery and of course computer vision. I mean, there's also this area of remote sensing, and I think Amin and I are having a discussion. What's, you know, where do you draw, you know, where do people in remote sensing, computer vision intersect? Or, you know, David or Andrew, do you have some thoughts on
David,
that?
you want to go first? I'm happy to.
Andrew, I was rather hoping you would, but
okay.
I don't really know the answer. I think what's happening now is vision is sort of a pool of technologies that is useful to everybody, well, to lots and lots of people. The sort of formal computer vision research community is huge, but I think if I think about sort of typical computer vision academic conferences, they don't usually have much in the way of remote sensing applications that appear at those conferences. But there clearly is a feed of information between the two communities, because a lot of remote sensing stuff is now benefiting from new detector technologies, new classification technology, and the like.
Yeah.
I'm not sure what the formal structure of that feed is. I think it may just be informal. People learn things and then use them on their own problems.
Yes, I think that's right, David. I mean, the thing that's, I think there was a moment reached in the last few years where you really saw sort of a convergence of enabling technologies. So first of all, we've opened up space. So we're now making literally the commercialization of low Earth orbit. And there are these self-compounding benefits to the continued reduction in launch costs that are putting more sensors on orbit, which are making more data available, which is actually introducing a host of interesting, it's eliminating some methodological questions. It's also introducing a whole host of new ones. So for example, on one side of that equation, the advent of cloud computing, large scale storage, and continuous remote sensing makes these very large data set, very high density time series data available. That's dramatically expanding the community of use. And it's also making many of the questions that you're asking, which I have to say, just the questions you're approaching, David, are absolutely salient. We deal with them every day because the sun is in slightly different places every single day, and you know, I literally was sitting there while you were giving your talk, you know, emailing snippets of what you were talking about, just in terms of dealing with variances in shading and shadows. And one of the major ways in which we're trying to figure out how to do that is the production of synthetic data sets that we can use to train better models, et cetera, et cetera. Those are all becoming practical questions. And then there is this other aspect, which is that no one has had continuous daily observations of the same place just from space at that particular, you know, from that particular vantage point. So now we have lots and lots and lots of very dense, high density time series data. And so that's represents, there are all kinds of questions about how do you fuse all of these different sensors to synthesize approaches to addressing questions of, you know, addressing shadows and other kinds of variability. There are questions about how do we use the time series itself to disambiguate any particular frame, and then kind of do that in all different temporal directions. All of that work is now practical because people both have the data and the platforms to use it. And so we have a program at Planet. I'll give a tiny plug. We give significant volumes of data away for free to every academic researcher who asks for it. We have a big education and research program. We have thousands of researchers, and I know dozens, and I've personally looked at dozens of computer vision papers that have been published on these questions. So I think the answer to Sanjay's question is things are dramatically improving. I might also just, if I could take the prerogative of having the screen for a moment. Julie, that was a great talk. Totally fascinating in lots of different directions. I wanted to ask you a question, which is about the 3 times per second update rate of the robot that's engaged in the collaborative task. And I wonder if you are discovering that there are rates below that where things sort of fall apart, or rates above that in terms of, updating policies around the observation of intent, where things kind of snap into focus. And I was thinking about 2 things there. One is just the things I know a little bit about proprioception, and I was trained as a cognitive scientist, and thinking about how we get feedback from our own bodies in space. And I think, signals move along our nerve pathways at like 80 milliseconds. So I'm thinking about this sort of the speed at which I personally would be updating my own policies of intention with the robot, doing the opposite. And I'm just curious about that dynamic interplay, if you've learned anything.
Yeah. So that 0.3 second update in the PumDP. So for the size of that model, that's quite fast. That's as pretty much as fast as we could get it on the particular computing platforms we were doing.
Right.
And for the pace of that task, it's all dependent on the pace of the task, but that's sufficient. It's by no means sufficient for a safety layer, for sure. So in our experiments, we have running underneath it a safety layer in which the robot slows and stops as the person nears. And early on in that work, much like the calculation you just went through, like 80 milliseconds, or like human reaction time is like 250 milliseconds.
Right.
I was so sure that 250 milliseconds was the appropriate time constant just for the safety layer. And I was proven wrong. So, like we have approval via our human subjects board for a person interacting within just a few centimeters of our dangerous industrial robot, the universal robot or the other collaborative robots, you can make contact with and they won't harm you. But we have a soft real-time system somewhere around a 7 millisecond loop time for a standard ABB industrial robot that you need running in the background as the safety layer. And we haven't done much work with contact in our lab. Many collaborative tasks do require contact, co-manipulating an object or manipulation of deformable materials or dressing a person is a newer one we're working with. And there, you're right. So the tactile, the force, torque feedback needs to be done at, and again, an entirely different time constant. And I think much like humans, this is, architecting those layers and those various time constants and how they interact is a key part of the system's challenge. So not useful for everything, but this particular task, it's suitable with that particular robot, etc.
That's great. Thank you.
Okay, thank you. Actually, there's one question from the audience from Hossein Akhlaqpur for Amin. Intuitively, I believe historical GPS trajectory normalized by width of the street is probably a good predictor for accidents. Can you use that to cross-check your model or?
Yes. Yeah, thank you very much. So actually, in fact, GPS trajectories are very effective in predicting accidents. And it's very interesting that one important information that GPS trajectories carry with them is basically how crowded some street or some intersection is. if some place is like more crowded, you of course are gonna observe more GPS trajectories there. So basically that's gonna give you an indication of how crowded some place is. And the level of crowdedness has a direct relationship with danger. So that's one way it helps, but it also helps because with GPS trajectories, you can figure out the speed, you can figure out acceleration, deceleration. With GPS trajectories, you can figure out whether one like piece of street is one way or two way, or whether most people turn left, or whether most people turn right, or 50% of the people, like whether there is actually a traffic light or not. All of those stuff can be seen within the information carried with GPS trajectories. So yes, they are actually quite effective.
Great. Thank you.
I want to also add something, Sanjay, to the thing that you asked about remote sensing and computer vision. I think a very fundamental difference is in remote sensing. Usually, the kind of data that people gather is already registered. So you know the coordinates of each piece of information that you get. That's usually the case with a very good, relatively good accuracy. And that way, the need for having models that are robust to deformation and having models that can basically register different things is less serious than in computer vision, where you deal with objects that move, objects that deform, objects that basically have a lot of complexities. And then, but actually, now that all of these machine learning tools are developed in computer vision, I think they have good applications in remote sensing. One, I think, very interesting example is what David talked about. You can use the same shading stuff and shadow, like removal stuff on satellite imagery. And if you want to, for example, track changes over time, you are interested in the intrinsic aspect of the image, not the extrinsic aspect. So if you can somehow separate the intrinsic aspect from the extrinsic aspect, you can simplify your process and basically become more robust to like all of these variations in shading and lighting conditions. And I really think that like they should be like people in remote sensing and computer vision should talk to each other more, and they should share with each other more.
I will second that thought. One thing that strikes me, so your remarks are interesting. One thing that strikes me that's an important difference is much of computer vision's activity is on sort of indoor scenes, and lighting in indoor scenes tends to be quite well behaved. You tend not to have very strong shadows. There tends not to be strong differences in illumination color in the shadow and outside shadow, that sort of thing. The sun and the sky are, in fact, quite complicated illuminates. You can usually know where the sun is, but the sky causes really significant changes in the color of cast shadows. And you get a variety of sort of funny effects that are not as common indoors. So to be honest, I think the intrinsic images stuff is highly relevant, but might require a little bit of sort of plumbing maneuvering to get it to work well outdoors because of how nasty the sky can be as an illuminant.
Yeah,
Right.
If I could just
questions here. Yeah.
David, you're so absolutely right. And we have literally, I could introduce you to a dozen engineers for whom that is the bane of their daily existence, right? Because you have, within a single constellation of satellites, you have slight variations between the radiometric calibration of the individual sensors. And then you have radically different daily conditions. And you have different conditions even within the same day, it's different to take a picture at 11:30 in the morning or 1 o'clock in the afternoon. We try to do it as close to noontime and on nadir, so looking straight down. But then you have wild variations across the Earth. So the way that much of that work is happening is through the application of AI to sensor fusion. So what we're doing is there are there are dozens of different satellite systems. Some of them are public, some of them are private, and we're interpolating and radiometrically cross-calibrating all of those things to some common standard, and then trying to apply that backwards and forwards in time. And so we're not applying the same level of computer vision techniques that you're describing here, but what we're trying to do is leverage the improved radiometric calibration of one sensor and apply it to pixels collected with another sensor, where the former might be more consistent, and then using some machine learning techniques basically to harmonize, and where we have gaps to sort of fill in all of those gaps. It's dramatically better than any one of the individual sensors, but it produces much more consistent results. But I am certain they could be substantially improved with techniques that are coming from your study.
So a rich source of really interesting effects is going to be the color of the sky, which changes from point to point. I lived for a while in Johannesburg, which has very substantial mine dumps. And what that means is very often the air has a large amount of very fine dust. The size of the dust particles depends a bit on the wind and the time of day and a bunch of other stuff. But what that means is you get the dramatic changes in sky color, meaning that essentially the color of everything you look at from space is going to change from day to day, and almost certainly from city to city, because of the changes in illumination color. That's something, by the way, where you could see properly constructed synthetic data being very helpful, and where, you know, there are methods in computer vision that might be exported and be helpful.
For sure.
So okay, great, thank you. So there's a question from Ram. So it's a more generic question, which I'm sure you have thought about. Will we see AI fatigue by project sponsors? So.
No.
I think we're just starting a bit.
Look, I mean, everything comes to an end, right? But there is very little evidence that it's a good thing to not understand these technologies very well. There's a great deal of evidence that understanding these technologies is a good way to build improvements in people's lives, build improved systems and objects and stuff. And it's kind of hard to believe that not knowing it makes life better. So no, I just don't see fatigue setting in anytime soon.
Julie, you have some thoughts on that, or?
Yeah, that's yeah, I guess when the question came up, I was thinking back to like when I started on the faculty, and there were so many faculty positions open. and back then I was thinking about robotics. I'm like, this won't last. This won't last. I hope my students, get great faculty positions. And it just, it keeps growing. And at MIT, we have the new Schwarzman College of Computing, and like a core part of the motivation of it is because computing is pervading, it's advancing the fundamentals of computing, but also bridging across the disciplines, because computing is such a core part of the advancement of many other engineering and scientific disciplines. I don't see this as a trend that's going away anytime soon. And for my own department in Aero Astro, there's a place to advance the fundamentals of computing, but when you're driven by the needs of a particular application area or domain area, that flows back to sort of change the path of innovation in the field more broadly, which I think is enormously valuable. It's kind of like a joke as a roboticist, like I can't make any use of these fancy like vision perception techniques. Like once you put it on a mobile robot, nothing works. And so, there's even in settings where, these systems perform very well, there's still, none of this is a solved problem, especially when you try to make it work in practice for particular applications. So I don't see it as a trend that's going away anytime soon.
Andrew and Amin, do you have some thoughts on that, or?
Andrew.
On AI fatigue?
Well, you know, if you want to think about investment fatigue, I think one very interesting example is ICOs in cryptocurrency, where there were a lot of frauds and basically really came to a very serious fatigue. But in the case of computer vision and machine learning, my belief is a lot of current investments could be due to lack of like understanding of the limit of computer vision and machine learning. But so it means that as people progress in understanding more and more the abilities of these tools, investors are going to be more informed in how they invest. So basically being able to solve a real problem and being able to generate real value, I think is going to is becoming a bigger and bigger factor in their decision making. But in general, I believe that machine learning and computer vision they have the potential to produce a lot of value. So it means that they're going to receive plenty of funding and investment in the future.
I maybe add to that just to say that, first of all, what's accelerating that we see is the pace of core fundamental research and its application, understanding its potential applications, to seeing, going from that pure research phase to, okay, now this is an algorithm on demand that's running in the cloud, that's, you know, piped via an API, is part of some industrial workflow. That process is actually collapsing in terms of the amount of time. And so the first thing is that I think the process of the digitization of the economy and of society is nowhere near complete. I think the economics are improving, the incentives are improving, the pace of innovation, the pace of transfer from research to application is accelerating. I think, candidly, the bigger conversation we need to have about many of these things is about the social contract, about data and AI ethics, about what we want rather than what can be done. And that conversation is even less developed as a society. I'll speak solely for my own.
So I want to second that and agree, you know, we do need to know what we want. One of the things that I think is very difficult in understanding these technologies is it can be quite hard to predict what the consequences of a particular technology are. The story I like to tell is about convolutional neural networks, which have been around since the year dot. Right, I had them in the first edition of the textbook, which I thought was very broad-minded of me, because, you know, what they were good at was classifying single handwritten letters, and I almost left it out of the second edition because they hadn't done anything else. And then a few years later, they just took off like a rocket. And I'm perfectly willing to believe that I'm bad at prediction, but I think everybody else is as well. It is difficult to look at a technology and say, it will have this impact.
Yeah.
And that's particularly true for ethical impacts, but it's also true for just straightforward, will it actually do anything? It is hard to do, and we undervalue how hard it is.
Dragos, you had a question, please?
Yeah, related to this and Julie and others. So, Julie, have you or anyone done a study? So you are studying mostly experts because experts have less uncertainty and they do things mostly in a certain way. Is there a limit in the uncertainty, in the noise that you know, if you draw a continuous scale, expert and totally amateur, is there a point there where we should stop, you know, actually observing people because we just cannot understand and model what they do because of the uncertainty and the noise and, you know, the inaccuracies?
Yeah. So in my research, generally, I do work with kind of expert populations, nurses, doctors, pilots, associates on an assembly line. But even within that context, you do have variation in performance and in ability to do a particular task. And it's not that it's invaluable to, it's not that, taking someone who is less proficient at a task and utilizing their demonstration, only harms your ability to learn. In fact, it can be very useful to learn from negative demonstrations. And from lower quality demonstrations as well, especially if you have, a quality assessment of that demonstration that's given. You think about it, one of the key things that you often want to learn is the delineation for acceptable versus unacceptable behavior. And there's, the best way to learn a delineation is to have examples from either side or from that broader space. So, and then another thing I've learned over the years from interaction with NASA and then in DoD applications is that one of the goals in those cases is not necessarily to improve the performance of a human or a human robot or human automated system, but that just aiming to reduce variation or variance in human behavior is a worthy goal. So NASA would much rather have less variance in astronaut performance in some science task than to be able to predict highly accurately whether they'll be able to do something well or less well. And then same thing in, for example, the Navy, where there's a lot of turnover. Every few months they turn over a whole ship. The goal of reducing variance or variation in human behavior is can be an end and can make the business case for introduction of that technology. And that's a different way of framing the objective for your AI or your decision support or your robot system.
Thank you. Taking learning a lesson from what David does, have you tried to, and okay, you learn a model of this, you learn basically a plan for, executing a task. Have you tried to correct that in places where we may have a good idea because we have prior knowledge? Like David knows, the probabilistic model between the albedo and so on. This is similar way you may know that, I don't know, executing, I don't know, a repair task, this should be followed by that, but nobody does it. So correcting your models using prior knowledge. Can you hear me?
Yeah. Anybody has a comment on that?
So the question was for Julie, maybe.
Oh.
Yeah.
Julie, you're muted.
Oh, sorry about that. Can you repeat the question? I'm sorry.
Would you be able, or have you tried to correct your models in places where you may have access to the optimal model of executing certain actions, and the ground truth or the way you observe people, you don't have that? You correct your model using prior knowledge in places.
Correct your model using prior knowledge. So
let's say there is a task, okay, that mechanics perform, and I don't know, getting from state 1 to state 3, they never do it in an optimal way, but that optimal way, or you can predict that optimal way.
Yeah. So one of the aspects we're interested in is how we can employ these systems to shape human behavior, to the point earlier about reducing variance, or if you via observation, you do know there is a more efficient way to perform assembly, and there is wide variation. Standard work doesn't mean it's actually done the same way from person to person, and small changes in that work actually can result in substantial inefficiencies in introduction of a robot to assist that work. And so shaping the person's ability to do the task into something that it has less variance or is more optimal is a significant area of interest for me. It's a newer area though. Our work most recently has been working on being able to develop personalized models with relatively little data on the semantic, temporal, and spatial aspects of performing a physical task as a first step towards that.
Okay. Thank you. Okay, I think great. Maybe it's time to wrap up. Thank you very much, everybody. And you know, the MLDAS continues for 2 more days. So I hope if you have time, you can come back and listen to the other talks. And hopefully sometime, come to Doha and visit us here. And hopefully, in the near future.
And what fun. It will be nice when the world allows us to do these kinds of things again.
That's right.
Thank you very much.
Thank you very much. Thanks.
What fun.
Appreciate it. Thank you. See you tomorrow.
Bye-bye.